The universe on its largest scales resembles a cosmic web, an intricate network of filaments, walls, clusters, and voids stretching across billions of light years. This structure emerged gradually over 13.8 billion years as gravity amplified tiny density variations present in the early universe. The cosmic web contains all the galaxies, gas, and dark matter in the observable universe, organized into a pattern that looks remarkably like foam, neural networks, or soap bubbles. Dense filaments containing galaxies and dark matter surround vast empty voids where few galaxies exist. The web's architecture reflects the fundamental processes that shape the universe, gravity pulling matter together while cosmic expansion stretches space apart. The cosmic web's discovery came through systematic galaxy surveys beginning in the 1980 seconds. The CFA Redshift survey conducted by Margaret Geller and John Huckra at the Harvard-Smithsonian Center for Astrophysics mapped thousands of galaxy redshifts measurements of how much their light has been stretched by cosmic expansion. By 1989, they had revealed the Great Wall, a sheet of galaxies spanning 500 million light-years across, but only 15 million light-years thick. This discovery shattered previous assumptions that galaxies distributed uniformly. Instead, galaxies clustered along thin structures surrounding empty regions. The pattern suggested that the universe had organized itself into a web-like structure of unprecedented scale. The Sloan Digital Sky Survey, or SDSS, which began observations in 2000 from Apache Point Observatory in New Mexico, revolutionized our understanding of large-scale structure. SDSS used a dedicated 2.5-meter telescope equipped with a 120-megapixel camera to photograph 1/4 of the sky. Spectrographs measured redshifts for over 930,000 galaxies, creating a three-dimensional map of cosmic structure spanning billions of light-years. The resulting images revealed the cosmic web in stunning detail. Galaxies trace thin filaments connecting massive clusters, while enormous voids occupy the spaces between. The largest structures in these maps span over 1 billion light-years, making individual galaxies appear as tiny dots within vast cosmic architecture. Filaments are the cosmic web's defining feature. These thread-like structures contain galaxies, hot gas, and dark matter stretched along lines connecting galaxy clusters. A typical filament extends 150 to 300 million light-years in length, but is only 20 to 30 million light-years wide, roughly 10 times longer than wide. Filaments contain approximately 60% of the universe's matter. Galaxies within filaments align along the filament's axis, suggesting that the filament's gravitational field influenced galaxy formation. The Milky Way lies within a filament connecting the Virgo cluster to the Fornax cluster, meaning our galaxy formed within one of these cosmic threads. Walls or sheets are two-dimensional surfaces where galaxies concentrate. These structures form at the intersection of multiple filaments, creating surfaces that can extend hundreds of millions of light-years in 2 dimensions, while being relatively thin, only tens of millions of light-years thick in the 3rd dimension. The CFA 2 Great Wall discovered in 1989 is a classic example, measuring 500 million by 200 million light-years, but only 15 million light-years thick. The galaxies in walls aren't uniformly distributed, but cluster along the wall's surface in groups and subclusters. Walls surround voids, forming the boundaries between empty regions and matter-filled regions. Clusters are the densest nodes in the cosmic web, locations where multiple filaments intersect. A galaxy cluster contains hundreds to thousands of galaxies bound together by gravity within a region 10 to 30 million light-years across. The Coma cluster contains about 1,000 large galaxies, plus countless smaller ones. Clusters sit at the intersections of filaments, like knots in a net. They represent the culmination of gravitational collapse. Matter flowed along filaments toward the densest regions, accumulating into clusters over billions of years. Clusters continue growing as galaxies and gas fall inward along the filaments feeding them. Voids are the empty spaces between filaments and walls, occupying roughly 80% of the universe's volume, but containing only 10 to 20% of galaxies. Typical voids measure 100 to 300 million light-years in diameter, though some exceed 1 billion light-years. The Boötes void, discovered in 1981, spans 330 million light-years and contains only about 60 galaxies, far fewer than the thousands expected in a typical region that size. Voids aren't completely empty, but are significantly underdense compared to average. Matter evacuated voids during cosmic evolution, migrating toward filaments and clusters, leaving behind sparse regions that expand faster than the cosmic average. The cosmic web's scale challenges human comprehension. The Milky Way galaxy measures 100,000 light-years across. Light traveling at 300,000 kilometers per second takes 100,000 years to cross it. The local group of galaxies containing the Milky Way, Andromeda, and about 80 smaller galaxies spans 10 million light-years, 100 times larger than the Milky Way. The Virgo supercluster containing the local group extends 100 million light-years, 10 times larger than the local group. The filaments and voids of the cosmic web span billions of light-years, 10 to 100 times larger than superclusters. Each scale increase represents structures built from smaller components. Galaxies form stars, groups form galaxies, clusters form groups, and the cosmic web organizes clusters. The cosmic web's formation began with tiny density variations in the early universe. The cosmic microwave background, emitted 380,000 years after the Big Bang, shows temperature fluctuations of 1 part in 30,000. These tiny differences corresponded to density variations in matter. Denser regions had slightly stronger gravity and attracted surrounding matter. Over time, gravity amplified these small differences. Denser regions became denser as they pulled in more matter, while underdense regions became more underdense as matter drained away. After billions of years of gravitational amplification, the tiny variations became the massive structures we see today: filaments, clusters, and voids, separated by factors of 10 or more in density. Dark matter plays a crucial role in cosmic web formation. Dark matter comprises 85% of the universe's matter and interacts only through gravity. It doesn't emit or absorb light, making it invisible, but its gravitational effects dominate structure formation. Computer simulations of cosmic web formation include dark matter as the primary component. The simulations show that dark matter collapses into filaments and halos, concentrated clumps where galaxies later form. Ordinary matter, gas and stars, follows the dark matter, falling into the gravitational wells created by dark matter concentrations. The cosmic web structure is fundamentally a dark matter structure, with visible galaxies tracing the underlying dark matter distribution. The cosmic web appears similar at different cosmic epochs, though with less contrast between dense and underdense regions at earlier times. Observations of distant galaxies show that filaments, walls, and voids existed when the universe was half its current age. The structures were less pronounced, density contrasts were smaller, filaments were thicker, and voids were smaller and less empty. As time progressed, gravitational collapse sharpened the contrasts, creating the well-defined web we see today. Future evolution will continue this trend until dark energy's accelerating expansion halts structure growth. Eventually, the web will freeze in its current configuration as expansion overwhelms gravitational collapse. The cosmic web's topology, its connectivity and shape, is a subject of ongoing research. Some regions have high connectivity, with many filaments meeting at clusters. Other regions have low connectivity, with isolated voids. The distribution of void sizes, filament lengths, and cluster masses follows statistical patterns that simulations must reproduce to validate cosmological models. The web's statistics depend on cosmological parameters, the amount of dark matter, dark energy, and ordinary matter, plus the initial amplitude and shape of density fluctuations. By comparing observed web statistics with simulations, cosmologists constrain these parameters, using the cosmic web as a laboratory for testing fundamental physics on the largest scales. The Virgo supercluster containing our local group. The Virgo supercluster is our cosmic neighborhood, a massive concentration of galaxy groups and clusters spanning 100 million light-years, with total mass approximately 100 trillion times the Sun's mass. The Milky Way resides in the outskirts of this supercluster, approximately 60 million light-years from its center. The Virgo supercluster contains at least 100 galaxy groups and clusters, including the local group containing the Milky Way, the Virgo cluster at the supercluster's center, and the Fornax cluster, Leo groups, and numerous smaller associations. This supercluster represents the gravitational basin within which our galaxy moves with falling toward the Virgo cluster's center at about 300 kilometers per second, drawn by its immense gravitational pull. Gérard de Vaucouleurs first identified the Virgo supercluster in 1953 through observations showing that galaxies in our region weren't distributed uniformly but concentrated toward the constellation Virgo. De Vaucouleurs noticed that the local group and surrounding galaxies formed a flattened distribution, a disk-like arrangement extending toward the Virgo cluster. He proposed that these galaxies belonged to a gravitationally bound system he called the local supergalaxy, or Virgo supercluster. Initial estimates suggested it contained about 100 galaxy groups with total mass around 100 trillion solar masses. Later observations refined these estimates, but confirmed the basic picture: we live in a large, gravitationally influenced region centered on the Virgo cluster. The Virgo cluster sits at the Virgo supercluster's center, approximately 54 million light-years from Earth in the constellation Virgo. The cluster contains over 1,300 galaxies. Some estimates reach 2,000 when including smaller dwarf galaxies, spread across a region roughly 15 million light-years in diameter. The cluster's brightest galaxy is Messier 87, or M87, a giant elliptical galaxy containing 1 trillion stars, 10 times more than the Milky Way. M87 hosts a supermassive black hole with mass 6.5 billion times the Sun's mass, famously imaged by the Event Horizon Telescope in 2019 as the first ever direct image of a black hole. The Virgo cluster's total mass is approximately 1.2 quadrillion solar masses, making it one of the nearest massive galaxy clusters. The local group, containing the Milky Way and Andromeda galaxies, lies on the Virgo supercluster's outskirts. The local group spans about 10 million light-years and contains approximately 80 known galaxies, most of which are small dwarf galaxies. The two dominant galaxies, the Milky Way and Andromeda, account for most of the group's mass. The local group is falling toward the Virgo cluster at about 300 kilometers per second, though the motion is complicated by additional gravitational influences from other structures. In roughly 4 billion years, the local group will have moved significantly closer to Virgo's center, though cosmic expansion driven by dark energy may prevent actual merger into the cluster. The Fornax cluster is another major component of the Virgo supercluster, located 62 million light-years away in the constellation Fornax. This cluster contains about 60 large galaxies within a region roughly 8 million light-years across. The Fornax cluster's most prominent member is NGC 1316, a giant elliptical galaxy showing evidence of recent merger activity. Tidal streams and shells of stars surrounding it indicate it consumed smaller galaxies within the past billion years. The Fornax cluster lies in a direction opposite to Virgo from the local group, meaning we're positioned between two major clusters within the supercluster. This location influences the local group's motion through space. The Leo groups, Leo Y and Leo 1-2, are additional components of the Virgo supercluster, located about 35 million light-years away. These groups contain several dozen galaxies each, including notable members like M65, M66, and NGC 3628, forming the Leo triplet. The Leo groups occupy the space between the local group and the Virgo cluster, contributing to the overall gravitational field that influences our motion. Detailed mapping shows that galaxies between the local group and Virgo aren't randomly distributed, but cluster in groups aligned along filaments connecting to the Virgo cluster's center. This demonstrates the hierarchical structure within the supercluster groups cluster into larger associations converging on the dominant Virgo cluster. The Virgo supercluster's shape is disc-like or pancake-like rather than spherical. The structure extends roughly 100 million light-years in its longest dimension, but is only about 10 to 15 million light-years thick. This flattened geometry reflects the anisotropic gravitational collapse that formed the supercluster matter, collapsed strongly along one or two directions, while remaining extended in the perpendicular direction. The Milky Way lies within this disk, meaning most of the supercluster's mass surrounds us in a plane. This geometry affects our motion. We're being pulled toward the Virgo cluster within the disk plane rather than perpendicular to it. The local sheet is a flat distribution of galaxies within the Virgo supercluster that includes the local group. The local sheet spans about 7 million light-years perpendicular to the sheet's plane, but extends much farther within the plane. It contains the local group, the Maffei group, the IC 342 group, and other nearby associations. The sheet lies between two voids, the local void on one side and a larger void on the other, giving it a location between underdense regions. This position within void's walls explains the local sheet's flattened shape galaxy formation, concentrated along the void boundaries where matter accumulated after evacuating the void interiors. The Virgo supercluster's mass distribution includes dark matter dominating the total mass, with visible galaxies tracing only 15% of the total. Observations of galaxy velocities within the supercluster show that galaxies move faster than visible matter alone could explain through gravity. The discrepancy indicates unseen mass dark matter providing additional gravitational force. Estimates suggest the Virgo supercluster contains roughly 100 trillion solar masses, most of which is dark matter. Hot gas filling the space between galaxies adds additional mass detected through X-ray observations, particularly in the dense Virgo cluster center where gas temperatures reach tens of millions of Kelvin, hot enough to emit copious X-rays. Our position in the Virgo supercluster affects astronomical observations. The concentration of galaxies toward Virgo creates the zone of avoidance, a region near the Milky Way's disk where dust in our galaxy blocks light from distant galaxies, making surveys incomplete. Additionally, our motion toward Virgo creates a dipole in the cosmic microwave background. The CMB appears slightly hotter in Virgo's direction and cooler in the opposite direction due to our motion relative to the CMB rest frame. This dipole, with amplitude about 3.3 millikelvins, reflects our velocity of 370 km per second relative to the CMB, which combines our orbital motion around the Milky Way, the Milky Way's motion within the local group, and the local group's motion toward Virgo. The Virgo supercluster's future evolution is uncertain due to dark energy. In a universe without dark energy, the supercluster would continue contracting as galaxies fell toward the Virgo cluster, eventually merging into a single giant cluster. However, dark energy causes cosmic expansion to accelerate, counteracting gravity on large scales. Current estimates suggest that structures larger than about 30 to 50 million light-years won't collapse. Further expansion will prevent them from merging. The Virgo supercluster spans 100 million light-years, probably too large to fully collapse. The local group will likely merge into a single galaxy as the Milky Way and Andromeda collide in 4 to 5 billion years. But the local group won't merge with the Virgo cluster. Instead, the space between them will continue expanding, eventually carrying Virgo beyond our observable horizon. The Virgo supercluster concept has evolved with new observations. Traditional definitions based on galaxy positions treated it as a gravitationally bound structure. However, modern measurements of galaxy velocities show that much of the supercluster isn't bound. Galaxies are moving apart with cosmic expansion, only slightly slowed by gravity. This realization led to the 2014 discovery that the Virgo supercluster is actually part of a larger structure called Laniakea, which will be discussed in the next chapter. The Virgo supercluster remains a useful concept for describing our local region, but it's now understood as a component of an even larger gravitational basin, rather than an isolated, bound system. Our cosmic address has expanded Milky Way, local group, Virgo supercluster, Laniakea supercluster, each level representing larger scales of cosmic organization. The Laniakea supercluster, discovered in 2014. Laniakea, meaning immeasurable heaven in Hawaiian, is the colossal structure containing the Virgo supercluster and defining our galaxy's motion through space. Discovered in 2014 by an international team led by R. Brent Tully from the University of Hawaii, Laniakea spans 520 million light-years in diameter and contains approximately 100,000 galaxies with combined mass roughly 100 million billion times the Sun's mass. Unlike previous supercluster definitions based on galaxy positions, Laniakea is defined by galaxy velocities. It represents the basin of attraction, where galaxies flow toward a common center. The Milky Way sits near Laniakea's edge, meaning our galaxy's motion through space is determined by gravitational attraction to mass within this immense structure. The discovery came from analyzing galaxy peculiar velocities, the component of galaxy motion not caused by cosmic expansion. Cosmic expansion causes galaxies to recede from each other with velocity proportional to distance, described by Hubble's law. But galaxies also have peculiar velocities, random motions caused by gravitational attraction to nearby mass concentrations, typically a few hundred kilometers per second. By measuring both the redshift from expansion and the peculiar velocity from gravitational motion, Tully and colleagues Hélène Courtois from the University of Lyon, Daniel Pomered from CEA Saclay, and Yehuda Hoffman from Hebrew University could map the gravitational flow of galaxies. They found that galaxies within a 520 million light-year region all flow toward a common attractor, defining Laniakea as the region dominated by this shared flow. The mapping technique used the Cosmic Flows 2 catalog, which compiled distance measurements for 8,000 galaxies. Accurate distances are crucial. Redshift alone doesn't reveal peculiar velocities, because redshift combines both expansion and peculiar motion. Independent distance measurements from methods like Tully-Fisher relation for spiral galaxies or surface brightness fluctuations for elliptical galaxies allow separation of expansion from peculiar velocity. The team used these distances to construct a velocity field showing how galaxies move relative to the overall expansion. Flow lines, similar to streamlines in fluid dynamics, showed where galaxies flow. Regions where flow converges define attractors. Boundaries, where flows diverge, define edges between different basins of attraction. Laniakea's center lies near the Norma cluster and Great Attractor region, about 250 million light-years from the Milky Way in the direction of the constellations Norma and Triangulum Australe. The Great Attractor is a gravitational anomaly identified in the 1,970 seconds when astronomers noticed that galaxies in our region, including the local group, are moving toward a point in this direction at velocities exceeding 600 kilometers per second. The Great Attractor's location behind the Milky Way's disk in the zone of avoidance, where dust blocks our view, made it difficult to observe directly. Later observations revealed the Norma cluster and several other massive galaxy clusters in this region, explaining the gravitational pull. Laniakea's definition finally placed the Great Attractor in context as part of the central concentration within a much larger basin. Laniakea contains several previously identified superclusters as components. The Virgo supercluster, our home, occupies Laniakea's outer regions. The Hydra Centaurus supercluster lies between us and Laniakea's center, containing the massive clusters Hydra, Centaurus, and Norma. The Pavo Indus supercluster forms another component. The southern supercluster adds additional mass. Each of these structures, previously thought of as separate superclusters comparable to Virgo, turns out to be part of Laniakea's gravitational basin. The realization that we're part of a much larger structure than previously recognized expanded our understanding of cosmic organization. Just as realizing the Milky Way is one galaxy among billions expanded our cosmic perspective, recognizing Laniakea expanded our understanding of the largest scales. The boundary between Laniakea and neighboring basins is defined by the surface where galaxy flows diverge. On one side, galaxies flow toward Laniakea's center. On the other, toward a neighboring structure's center. These boundaries aren't physical barriers, but represent the dividing surfaces in the cosmic velocity field. Laniakea's neighbors include the Shapley supercluster, an even more massive concentration about 650 million light-years away, that will be discussed later, and the Perseus-Pisces structure in another direction. The boundaries between these basins fluctuate slightly depending on local density variations, but define relatively stable separations between distinct gravitational domains. The structure's discovery resolved long-standing questions about the local group's motion. Observations showed the local group moving at 630 kilometers per second relative to the cosmic microwave background rest frame toward a point called the CMB dipole direction. This motion results from gravitational attraction to mass concentrations in that direction. Before Laniakea's discovery, the responsible mass wasn't fully identified. The Virgo cluster alone couldn't explain the full velocity. The Great Attractor provided part of the answer, and the Shapley supercluster beyond Laniakea contributed additional pull. Laniakea's definition clarified that our velocity results from falling through Laniakea's gravitational basin toward its center, while simultaneously being pulled by Shapley supercluster's gravity beyond Laniakea's edge. Laniakea's mass is approximately 100 million billion solar masses, written as 10 to the 17th solar masses. This includes dark matter, which dominates the total mass, plus ordinary matter in galaxies and hot gas. The 100,000 galaxies within Laniakea each contain hundreds of billions of stars on average, giving roughly 10 trillion stars total, a 1 followed by 25 zeros. However, stars contribute only a small fraction of the total mass. Dark matter outweighs ordinary matter by roughly 5 to 1, meaning about 80% of Laniakea's mass is dark matter. The remaining ordinary matter divides between stars in galaxies, gas within galaxies, and hot intergalactic gas-filling space between galaxies. The discovery method defining structures by velocity fields rather than density represents a new approach to mapping cosmic structure. Previous supercluster definitions relied on identifying regions with high galaxy density, but density alone doesn't indicate gravitational binding or common origin. Velocity fields reveal dynamical relationships which structures influence each other gravitationally. The technique has been applied to map other basins of attraction beyond Laniakea, revealing that the observable universe contains numerous such structures, each representing a region where galaxies share common gravitational influence. This dynamical view of structure is more physically meaningful than simple density-based definitions. Laniakea's discovery utilized advanced visualization techniques. Daniel Pomered created three-dimensional visualizations showing galaxy positions colored by velocity, with flow lines indicating motion. These visualizations, released publicly in 2014 and widely distributed in astronomy media, made the structure immediately comprehensible. Viewers could see how galaxies throughout a 520 million light-year volume all flow toward a common center, with boundaries marking where flows separate toward different attractors. The visualizations demonstrated how modern data visualization helps astronomers understand complex, three-dimensional cosmic structures that would be incomprehensible from tables of galaxy positions and velocities alone. The scale of Laniakea is staggering. Light takes 520 million years to cross it, meaning we see opposite edges as they were when Earth was in the Cambrian period, 520 million years ago, when complex life was just diversifying. The structure's age is nearly as old as the universe itself. It began forming from tiny density fluctuations present 13.8 billion years ago, and grew through gravitational collapse over cosmic history. Laniakea likely represents one of the largest structures that will ever form dark energy's acceleration, prevents new structures larger than a few 100 million light-years from collapsing. Existing structures like Laniakea will persist, but won't grow much larger. Laniakea represents the universe's organizational hierarchy, at scales approaching the cosmological principle's limit, beyond which the universe becomes homogeneous and loses structure. Our position near Laniakea's edge, rather than its center, is statistically expected. Most volume in any large structure lies near the edges rather than the center. Simple geometry shows that in a sphere, the outer half of the radius contains 87.5% of the volume. Observers placed randomly within Laniakea are far more likely to find themselves in the outer regions than near the center. Nevertheless, the edge location has implications. We're moving inward toward Laniakea's center, meaning our position will shift over cosmic time. In several billion years, the Milky Way will be closer to Laniakea's center, though dark energy's acceleration may prevent ever reaching the very center. Our descendants, if they still observe the cosmos billions of years hence, will inhabit a different location within cosmic structure, the Shapley supercluster pulling our local region. The Shapley supercluster, named after Harlow Shapley, who first noted the concentration of galaxies in this region, in the 1,930 seconds, is the most massive known structure in the nearby universe. Located approximately 650 million light-years away toward the constellations Centaurus and Hydra, the Shapley supercluster contains an estimated 10 million billion solar masses, 10 times more massive than Laniakea. This immense concentration includes over 25 rich galaxy clusters and thousands of individual galaxies packed into a region roughly 300 million light-years across. The Shapley supercluster's enormous mass generates gravitational pull that influences galaxy motion across hundreds of millions of light-years, including contributing to the local group's velocity of 630 kilometers per second toward the so-called Great Attractor region. The supercluster's core consists of several extremely massive galaxy clusters. The richest is Abell 3558, which contains hundreds of galaxies within a 10 million light-year region and has total mass approximately 2 quadrillion times the Sun's mass. Abell 3558 is the central cluster of the Shapley concentration, the densest part of the supercluster where multiple clusters merge. Other major clusters include Abell 3562, Abell 3556, and Abell 3571, each containing hundreds of galaxies and masses exceeding 1 quadrillion solar masses. These clusters lie within about 50 million light-years of each other and are gravitationally interacting. They're in the process of merging into an even more massive structure over the next few billion years. Though dark energy's acceleration may prevent complete merger, X-ray observations from satellites like Chandra and XMM Newton reveal hot gas permeating the Shapley supercluster. This gas, heated to temperatures between 10 million and 100 million Kelvin, emits X-rays detectable from Earth. The gas fills the space between galaxies in the clusters and extends into the filaments connecting clusters. The gas's temperature and distribution map the supercluster's gravitational potential. Hotter gas concentrates in deeper potential wells. X-ray observations show that the Shapley concentration's clusters are embedded in a common envelope of hot gas, indicating they're part of a single system rather than isolated structures. The gas mass adds significantly to the supercluster's total mass, though it's still far less than the dark matter dominating the gravitational field. The Shapley supercluster's discovery as a major mass concentration came gradually. Harlow Shapley identified the region as having an unusually high density of galaxies in the 1930 seconds, but its distance and extent weren't well established until the 1980 seconds. Redshift surveys in the 1980 seconds and 1990 seconds by teams including Roberto Scaramella and colleagues confirmed that hundreds of galaxies in this region shared similar redshifts around z equals 0.046, corresponding to distance approximately 650 million light-years. This confirmed the concentration as a physical structure rather than a chance alignment. Further surveys revealed that the structure extended over tens of degrees on the sky and contained multiple rich clusters, making it the largest concentration of mass in the nearby universe. The Great Attractor phenomenon relates closely to the Shapley supercluster. In the 1970 seconds and 1980 seconds, astronomers analysing galaxy velocities noticed that galaxies in our region, including the local group, are moving toward a point in the sky at about 630 kilometers per second, after accounting for cosmic expansion. This point, dubbed the Great Attractor, lies in the direction of the Hydra and Centaurus constellations, frustratingly behind the Milky Way's disk, where dust obscures our view. Initial observations identified several massive clusters in this direction, at distances around 200 to 250 million light-years, including the Norma cluster and clusters in Centaurus. These structures contribute to the gravitational pull, but their mass alone couldn't fully explain the local group's velocity. The realization that the Shapley supercluster contributes significantly to our motion-resolved part of the Great Attractor puzzle. Although Shapley lies 650 million light-years away, about 3 times farther than the Great Attractor region, its mass is so enormous that its gravitational pull remains significant even at our location. Computer simulations of large-scale flows show that the local group's motion results from a combination of sources, the Virgo cluster and Laniakea pulling us inward, the Great Attractor clusters at 250 million light-years providing intermediate pull, and the Shapley supercluster at 650 million light-years contributing substantial long-range attraction. The velocity vector results from vector addition of all these pulls, with Shapley's contribution being perhaps 25% of the total velocity. The Shapley supercluster lies beyond Laniakea's boundary, meaning it represents a separate basin of attraction. Galaxies within Shapley flow toward its center, not toward Laniakea's center. The boundary between Laniakea and Shapley, a surface where velocity flows diverge, lies approximately 400 to 450 million light-years from the Milky Way. Galaxies on our side of the boundary flow toward Laniakea's center in the Norma region. Galaxies beyond the boundary flow toward Shapley's center. Despite this dynamical separation, Shapley's gravity still influences our motion, because gravity has infinite range, even across the boundary. Shapley's mass pulls on Laniakea's contents, contributing to the overall flow pattern. This demonstrates that supercluster basins aren't completely isolated, but interact gravitationally across their boundaries. The Shapley supercluster's structure includes multiple filaments converging on its core. Galaxy surveys show that galaxies stream along filaments toward the Shapley concentration from all directions. These filaments connect Shapley to other structures across hundreds of millions of light-years, integrating it into the cosmic web. One filament connects to the Horologium Reticulum supercluster, another to the Microscopium supercluster. These connections demonstrate that even the largest structures aren't isolated islands, but nodes in a network spanning the observable universe. Matter flows along filaments toward massive clusters, with Shapley being one of the largest sinks in the cosmic flow. The supercluster's age is comparable to the universe's age. Structure formation simulations show that concentrations like Shapley began forming from initial density fluctuations present 13.8 billion years ago when the universe began. Initially, the fluctuations were tiny, only 1 part in 30,000 density variation. Over billions of years, gravity amplified these fluctuations. Denser regions attracted surrounding matter, growing denser still. By the time the universe was a few billion years old, the first galaxy clusters had formed in the densest regions. Over subsequent billions of years, these clusters fell toward each other along filaments, assembling into superclusters. Shapley represents one of the most successful instances of this assembly, a location where an unusually large initial overdensity grew into the most massive structure in the nearby universe. Shapley's mass makes it interesting for dark matter studies. The supercluster's gravitational effects on galaxy motions reveal the total mass distribution, including dark matter. By comparing X-ray observations showing hot gas distribution with optical observations showing galaxy positions and gravitational lensing revealing total mass, astronomers can map how dark matter distributes within the supercluster. Results show dark matter halos surrounding each cluster, plus additional dark matter filling filaments between clusters. The mass distribution follows predictions of cold dark matter simulations, where dark matter collapses into halos and filaments, with ordinary matter following. Shapley serves as a laboratory for testing dark matter physics on supercluster scales. The Shapley supercluster's future evolution depends on the competition between gravity and dark energy. If gravity dominates, the supercluster will continue collapsing. Its clusters will merge over tens of billions of years into a single giant cluster, perhaps reaching total mass 10 to 20 million billion solar masses. However, dark energy's acceleration counteracts gravity. Current understanding suggests that structures larger than about 100 to 200 million light-years won't collapse. Further expansion prevents complete merger. Shapley spans 300 million light-years, possibly too large to fully collapse. The central Shapley concentration will likely merge into a single cluster, but outlying clusters may never reach the center. Instead, the supercluster will freeze in a partially collapsed state as dark energy increasingly dominates, eventually tearing apart the outer regions while the core remains bound. Observing the Shapley supercluster provides insights into large-scale structure formation. Its existence demonstrates that the universe can form structures with 10 million billion solar masses within 13.8 billion years, starting from tiny initial fluctuations. This constrains cosmological models, the amplitude of initial fluctuations, the amounts of dark matter and dark energy, and the universe's expansion history must all conspire to allow Shapley mass structures to form. If initial fluctuations were smaller or dark energy stronger, such massive structures couldn't exist. Conversely, if fluctuations were larger, even bigger structures would exist. Surveys counting structures like Shapley at different distances probe cosmic history, testing whether structure formation proceeded as lambda CDM predicts. So far, observations match predictions, supporting the standard model. The Sloan Great Wall spanning 1.4 billion light-years. The Sloan Great Wall is one of the largest structures ever discovered in the universe, spanning 1.37 billion light-years in its longest dimension. Discovered in 2003 by J. Richard Gott III and Mario Jurich of Princeton University, analyzing data from the Sloan Digital Sky Survey. This immense structure consists of multiple superclusters of galaxies connected by filaments, forming a coherent wall-like arrangement. The structure lies at an average distance of approximately 1 billion light-years from Earth, corresponding to redshift Z, approximately 0.073, meaning we see it as it appeared 1 billion years ago when light now reaching us began its journey. The Sloan Great Wall contains thousands of galaxies with combined mass estimated at millions of billions of times the Sun's mass, making it one of the most massive structures known. The discovery emerged from systematic analysis of SDSS galaxy positions. The Sloan Digital Sky Survey mapped over 930,000 galaxies by 2003, measuring their positions and redshifts to create three-dimensional maps. Gott and Jurich applied algorithms to identify overdense regions, areas with significantly more galaxies than average. They found that galaxies at redshift around 0.073 concentrated along a curved, elongated structure stretching across roughly 60 degrees of sky. Converting angular size and redshift to physical dimensions showed the structure extended 1.37 billion light-years long, 250 million light-years wide, and about 100 million light-years thick. The discovery paper, published in the Astrophysical Journal, noted that structures this large to approach the scale where the cosmological principle, the assumption that the universe is homogeneous on large scales, should apply. The Sloan Great Wall shape resembles a slightly curved wall or sheet rather than a spherical cluster. This geometry reflects how gravitational collapse occurs in 3 dimensions. When matter collapses gravitationally from an initially random distribution, it doesn't collapse uniformly in all directions. Instead, collapse proceeds fastest in the directions where compression is strongest, typically 2 directions, while the third direction remains extended. The result is sheet-like or wall-like structures, 2-dimensional surfaces where matter concentrates. The Sloan Great Wall represents such a sheet, formed as matter flowed together along filaments from 2 directions while remaining spread out in the third direction. Galaxies within the wall aren't uniformly distributed, but cluster in groups and subclusters along the wall's surface. The structure includes several previously known rich galaxy clusters. The Corona Borealis supercluster, identified before the Sloan Great Wall's discovery, lies within it at approximately the same redshift. This supercluster contains several rich clusters, including Abell 2065, Abell 2061, and Abell 2089, each hosting hundreds of galaxies. The inclusion of these clusters within the larger Sloan Great Wall structure demonstrates that what were previously thought of as separate superclusters actually form components of an even larger, coherent structure. This hierarchical organization, galaxies cluster into groups, groups cluster into clusters, clusters connect into superclusters, and superclusters link into great walls, characterizes cosmic structure across all scales, from millions to billions of light years. The Sloan Great Wall's mass is difficult to determine precisely because the structure isn't gravitationally bound. Unlike galaxy clusters, where all members orbit a common center, the Sloan Great Wall's galaxies are moving apart with cosmic expansion, only slightly slowed by mutual gravity. This means the structure isn't a bound object destined to collapse, but rather a coherent overdensity embedded in the expanding universe. Mass estimates based on galaxy counts and galaxy masses suggest total mass in the range of millions of billions of solar masses, but the exact figure depends on assumptions about dark matter distribution. The structure's significance lies more in its length than its total mass. It demonstrates that coherent structures can extend over more than 1 billion light-years despite cosmic expansion. The discovery raised questions about the cosmological principle. This principle states that on sufficiently large scales, typically considered to be above 300 to 400 million light-years, the universe should appear homogeneous and isotropic, meaning the distribution of matter is uniform and the same in all directions. Structures exceeding 1 billion light-years challenge this assumption because they introduce inhomogeneities on scales comparable to the scale where homogeneity should dominate. However, the cosmological principle refers to average density fluctuations around the average can be large on smaller scales. Statistical analysis shows that structures like the Sloan Great Wall are rare but not impossible in the standard cosmological model. Their existence doesn't require abandoning the cosmological principle, but does push its applicability to larger scales. Comparison with earlier discovered walls provides context. The CFA-2 Great Wall, discovered in 1989 by Margaret Geller and John Huckra, spans about 500 million light-years, roughly 1/3 the Sloan Great Wall's length. The CFA-2 wall lies much closer, at about 200 million light-years distance, making it easier to study in detail. Both structures show similar morphology, thin sheets of galaxies surrounding voids. The Sloan Great Wall's greater size likely reflects the larger volume sampled by SDSS compared to earlier surveys. As surveys extend to greater distances and volumes, larger structures are discovered simply because more space is surveyed. This suggests that structures even larger than the Sloan Great Wall might exist at greater distances, awaiting discovery by future surveys. The structure's formation traces back to the early universe's density fluctuations. Measurements of the cosmic microwave background show that when the universe was 380,000 years old, density variations of 1 part in 30,000 existed on all scales. These variations provided the seeds for structure formation. Regions with above-average density had stronger gravity and attracted surrounding matter. Over billions of years, gravity amplified the variations. By the time the universe was a few billion years old, the densest regions had collapsed into the first galaxies and clusters. By 1 billion years ago, the epoch when we observed the Sloan Great Wall, the structure had assembled into its current configuration through billions of years of gravitational attraction and gas infall along filaments. The Sloan Great Wall's age means we observe it when the universe was 12.8 billion years old, about 93% of its current age. At that epoch, the universe was denser, expanding faster, and structure formation was more active than today. Dark energy comprised a smaller fraction of total energy density, meaning gravity was relatively stronger compared to now. These conditions allowed structures to continue growing that would now be frozen by dark energy's acceleration. The Sloan Great Wall represents a snapshot of cosmic structure near the transition from the matter-dominated era, when structures actively grew, to the dark energy-dominated era beginning around 5 billion years ago, when structure growth slowed. Comparing structures at different epochs reveals how structure formation has evolved as dark energy became increasingly dominant. Statistical analysis of structure sizes is crucial for testing cosmological models. The abundance of structures at different scales, how many clusters, superclusters, and great walls exist in a given volume, depends on cosmological parameters. Too many large structures would indicate that initial density fluctuations were larger than CMB measurements suggest, or that gravity is stronger than general relativity predicts. Too few would suggest the opposite. The Sloan Great Wall's existence is consistent with lambda CDM predictions, though it lies near the upper end of expected structure sizes. Computer simulations of cosmic structure formation in lambda CDM occasionally produce structures of similar size, confirming that such structures can form within standard cosmology without requiring new physics. The structure's discovery demonstrates the power of large-scale surveys. The Sloan Digital Sky Survey observed 1/4 of the sky, mapping roughly 1 billion cubic light-years of space. This enormous volume allowed detection of rare, large structures like the Sloan Great Wall that wouldn't appear in smaller surveys. Future surveys, like the Dark Energy Spectroscopic Instrument, or DESI, which began observing in 2021, will map tens of millions of galaxies across even larger volumes, likely discovering additional great walls and potentially structures even larger than Sloan. Each new generation of surveys extends our view deeper into space, revealing the universe's structure on progressively larger scales and testing whether cosmic homogeneity truly emerges at the largest scales as the cosmological principle predicts. The Sloan Great Wall exemplifies the cosmic web's largest features. While filaments connect clusters across hundreds of millions of light-years and superclusters span similar scales, great walls represent the ultimate expression of sheet-like structure formation. They form at the intersections of multiple filaments, where matter from numerous sources converges. The Sloan Great Wall likely marks the interface between multiple large voids regions, where matter evacuated, concentrating at the void boundaries. This wall and void pattern characterizes the cosmic web at its largest scales. Understanding how these structures formed, why they reach certain sizes, and how they evolve provides insights into the fundamental processes governing the universe's large-scale organization. The Hercules Corona Borealis Great Wall at 10 billion light-years. The Hercules Corona Borealis Great Wall is claimed to be the largest known structure in the observable universe, allegedly spanning approximately 10 billion light-years across. Discovered in 2013 by István Horváth and colleagues at the National University of Public Service in Hungary through analysis of gamma-ray burst distributions, the structure, if real, would extend across roughly 1/10 of the observable universe's diameter. The structure lies at an average redshift of approximately Z equals 1.6 to 2.1, corresponding to distances between 9 and 10 billion light-years, meaning we observe it as it appeared when the universe was only 3 to 4 billion years old, less than 30% of its current age. However, the structure's existence remains controversial, with many astronomers questioning whether it represents a genuine physical structure or a statistical artifact. The discovery came from mapping gamma-ray bursts, extremely energetic explosions that occur when massive stars collapse or neutron stars merge. Gamma-ray bursts are among the brightest events in the universe, visible across billions of light-years, making them useful as tracers of matter distribution at great distances. Horváth and his team analysed 283 gamma-ray bursts from the SWIFT satellite's catalogue, measuring their positions and redshifts. They found that gamma-ray bursts in a region centred on the border between the Hercules and Corona Borealis constellations appeared more densely clustered than expected by chance. Statistical tests suggested that roughly 14 to 19 gamma-ray bursts in this region formed a coherent group at similar redshifts around Z equals 2, indicating a possible overdensity of galaxies spanning an enormous volume. The claimed size 10 billion light-years makes the structure extraordinary. For comparison, the Sloan Great Wall spans 1.37 billion light-years and was considered extremely large. The Hercules Corona Borealis Great Wall would be more than 7 times longer, containing volume roughly 400 times greater. At 10 billion light-years across, the structure spans about 10% of the observable universe's 3 billion light-year diameter. If it exists, the structure approaches the scale where the cosmological principle absolutely must apply. The universe should be homogeneous on scales above a few billion light-years. A 10 billion light-year structure pushes or potentially exceeds this limit, challenging foundational assumptions of cosmology. The cosmological principle problem is the primary reason many astronomers remain skeptical. The principle states that the universe is homogeneous and isotropic on scales larger than about 300 to 400 million light-years above this scale. Matter should be uniformly distributed on average. This principle is foundational to modern cosmology, underlying the Friedmann equations describing cosmic expansion and the interpretation of the cosmic microwave background. A structure 10 billion light-years across introduces inhomogeneity on scales where homogeneity should dominate. While rare fluctuations around average density are expected, a structure this large would be so rare in standard cosmology that its existence might suggest the cosmological principle breaks down or that cosmological models need revision. The statistical significance of the detection is marginal. The original paper reported a significance of approximately 3 to 4 sigma, meaning there's roughly 1 inch 1,000 to 1 inch 15,000 chance the clustering occurred randomly. While this seems impressive, particle physics and astronomy typically require 5 sigma significance, 1 inch 3.5 million chance before claiming discovery. The 3 to 4 sigma level often produces false positives. Additionally, the analysis involved searching for clusters across many regions of sky and many redshift ranges, which increases the probability of finding apparent clusters by chance. The multiple comparisons or look elsewhere effect. When accounting for this effect, the true significance might be lower than reported. Subsequent analyses have questioned the structure's reality. Independent teams reanalyzing gamma-ray burst distributions found weaker evidence for the clustering. Some studies found no statistically significant overdensity in this region once selection effects and biases were properly accounted for. Others found that the apparent structure disappears when using slightly different analysis methods or when including additional gamma-ray bursts from later observations. The controversy reflects a fundamental challenge in large-scale structure studies. With limited data and complex statistical analysis, distinguishing genuine structures from statistical fluctuations or systematic errors is difficult. Many claimed large structures have later been debunked or reduced in significance as more data and better analysis techniques became available. Gamma-ray bursts, as tracers of large-scale structure, have limitations. Gamma-ray bursts trace star formation in massive galaxies, which correlates with, but doesn't perfectly track total matter distribution. Dark matter, comprising 85% of matter, is invisible if we infer its presence from gravitational effects on visible matter. Gamma-ray bursts trace only a specific subset of visible matter. Additionally, gamma-ray bursts are rare events. Only a few dozen occur per day across the entire observable universe. With only 283 gamma-ray bursts used in the original analysis, the sample is sparse. Sparse sampling makes it difficult to distinguish real structures from chance alignments. Galaxy surveys using millions of galaxies provide much better structure mapping, but don't reach the distances where the Hercules Corona Borealis Great Wall supposedly lies. The structure's physical nature, if it exists, would be different from nearby structures like the Sloan Great Wall. At redshift Z equals 2, the universe was only 3.3 billion years old, 1/4 its current age. The universe was denser, hotter, and expanding faster. Structure formation was still actively proceeding. The largest structures were smaller than today. The cosmic web at Z equals 2 had thinner filaments, smaller voids, and less pronounced density contrasts than today. An overdensity spanning 10 billion light-years at Z equals 2 would represent an extraordinarily rare fluctuation, perhaps the largest structure that could form in the standard cosmological model. Understanding how such a structure could form within lambda CDM requires detailed simulations that can barely resolve such rare events. Alternative explanations for the gamma-ray burst clustering include projection effects. The structure might not be a single coherent object, but multiple, smaller structures at slightly different distances that happen to align along our line of sight, creating the illusion of a single, enormous structure. Projection effects are common in astronomy. The constellation Orion appears as a coherent pattern, but its stars lie at vastly different distances, with no physical connection. Similarly, the apparent gamma-ray burst overdensity might result from several unrelated galaxy concentrations aligned by chance. Distinguishing true structures from projection effects requires precise redshift measurements and three-dimensional mapping, which is challenging for distant gamma-ray bursts where redshift uncertainties can be several percent. Even if the structure is real, its name might be misleading. The term Great Wall implies a coherent wall-like structure similar to the Sloan Great Wall or CFA2 Great Wall, but the Hercules Corona Borealis overdensity might be more diffuse, a loose association of galaxy clusters and filaments rather than a well-defined wall. At the distances and epochs involved, expecting structures with morphologies similar to nearby Great Walls might be unrealistic. The structure could represent a different class of object, perhaps a supercluster complex, or a region where multiple filaments intersect rather than a wall-like sheet. Clarifying the structure's nature requires better observations, including deep galaxy surveys and spectroscopic mapping of the region. Future observations might resolve the controversy. The Dark Energy Spectroscopic Instrument, or DESI, is conducting spectroscopic surveys of millions of galaxies at redshifts Z equals 1 to 2, precisely the range where the Hercules Corona Borealis Great Wall supposedly lies. DESI will map the three-dimensional distribution of galaxies with much better sampling than possible with gamma-ray bursts alone. If a genuine overdensity exists in this region, DESI will detect it definitively. If the gamma-ray burst clustering was statistical artifact or projection effect, DESI will show no corresponding galaxy overdensity. Results from DESI's first few years of observations will likely settle the question of whether the Hercules Corona Borealis Great Wall is a real structure or an illusion created by sparse sampling and marginal statistics. The controversy surrounding the Hercules Corona Borealis Great Wall illustrates challenges in large-scale structure research. As surveys push to greater distances and larger scales, the number of independent samples decreases. There are only so many billion light-year volumes in the observable universe. With limited samples, rare fluctuations become more likely, and distinguishing genuine structures from statistical flukes becomes harder. The largest structures are also the rarest, making statistical tests less powerful. Furthermore, at great distances, observations become more difficult and uncertain, adding noise that complicates analysis. These challenges mean that extraordinary claims about structures near the limits of the observable universe require extraordinary evidence. The Hercules Corona Borealis Great Wall remains a fascinating candidate, but awaits confirmation by independent observations before being accepted as definitively real. The Boss Great Wall from Baryon Oscillation Survey. The Boss Great Wall is one of the largest confirmed structures in the universe, discovered in 2016 through analysis of data from the Baryon Oscillation Spectroscopic Survey. The structure spans approximately 1 billion light-years in length and 820 million light-years in width, with thickness of about 170 million light-years. Located at redshift Z approximately 0.47, corresponding to distance roughly 5 billion light-years from Earth, the Boss Great Wall appears, as we observe it, when the universe was 8.8 billion years old, about 64% of its current age. The structure consists of multiple superclusters connected by filaments, forming a massive wall-like concentration of galaxies containing an estimated mass of several billion times the Sun's mass. The discovery came from the Baryon Oscillation Spectroscopic Survey, or BOSS, which operated from 2009 to 2014 as part of the Sloan Digital Sky Survey 3. BOSS measured redshifts for 1.5 million galaxies across 10,000 square degrees of sky, creating the largest three-dimensional map of cosmic structure ever made at the time. Heidi Lietzen and colleagues at the Instituto de Astrofísica de Canarias in Spain analyzed the BOSS data, searching for galaxy overdensities, regions with significantly more galaxies than the cosmic average. They identified a massive structure at Z equals 0.47, containing numerous rich galaxy clusters and superclusters connected by filaments. The structure's scale and coherence rivaled the Sloan Great Wall, making it one of the largest confirmed structures known. The Boss Great Wall structure includes at least 5 major superclusters. Each supercluster contains multiple galaxy clusters, dense concentrations of hundreds of galaxies bound by gravity. The superclusters connect through filaments, thread-like structures containing galaxies and dark matter. The arrangement forms a wall-like sheet separating 2 large voids regions containing fewer galaxies than average. The wall's morphology reflects the cosmic web's hierarchical organization. Galaxies cluster into groups, groups cluster into clusters, clusters connect into superclusters, and superclusters form great walls. The Boss Great Wall represents one of the cosmic web's largest nodes, where numerous filaments converge and matter has concentrated over billions of years. The structure's discovery utilized sophisticated analysis techniques. Simply counting galaxies isn't sufficient to identify structures, because the galaxy distribution appears lumpy, even if galaxies are randomly distributed. Random distributions always show some clustering by chance. Statistical tests must determine whether observed clustering exceeds random expectations. Lietzsen's team used the Friends of Friends algorithm, which groups galaxies closer than a specified separation, plus additional tests comparing observed galaxy density to density in simulated random distributions. The analysis showed that galaxies in the Boss Great Wall region were clustered more tightly than 99.9% of random distributions, confirming the structure is statistically significant rather than a chance alignment. The mass of the Boss Great Wall is estimated at approximately 10 to 20 million billion solar masses. This estimate comes from multiple methods. Counting galaxies and multiplying by average galaxy mass gives a baseline, but this includes only visible matter, stars, and gas in galaxies. Dark matter dominates the total mass, outweighing visible matter by roughly 5 to 1. Measuring galaxy velocities reveals the total mass, including dark matter, through the virial theorem. Faster velocities indicate stronger gravity and more mass. Gravitational lensing the bending of light from background galaxies by the structure's gravity provides another mass estimate. These methods agree within uncertainties, giving confidence that the total mass is several million billion solar masses, comparable to other Great Walls. The Boss Great Wall's distance places it at an interesting epoch in cosmic history. At redshift Z equals 0.47, the universe was 8.8 billion years old. This was near the transition from the matter-dominated era, when gravity drove structure formation, to the dark energy-dominated era, beginning around 6 to 5 billion years ago, when accelerating expansion began slowing structure growth. The Boss Great Wall formed during the peak era of structure formation, when the largest structures could still actively grow through gravitational collapse. Structures forming later, in the dark energy-dominated era, grew more slowly and reached smaller maximum sizes. The Boss Great Wall represents one of the last Great Walls to form before dark energy shut down large-scale structure formation. Comparison with other Great Walls provides context for understanding cosmic structure. The Sloan Great Wall, at 1.37 billion light-years long and distance 1 billion light-years, is slightly longer but closer. The CFA 2 Great Wall, at 500 million light-years long and distance 200 million light-years, is significantly smaller and closer. The controversial Hercules Corona Borealis Great Wall, if real, would be much larger at 10 billion light-years across, but lies much farther at 10 billion light-years distance and has questionable reality. The Boss Great Wall ranks among the largest confirmed structures, being one of the few structures exceeding 1 billion light-years in any dimension. Its size approaches but doesn't exceed theoretical limits from the cosmological principle, making it large but not impossibly so within standard cosmology. The structure's formation history can be inferred from cosmological simulations. Structures like the Boss Great Wall originate from density fluctuations in the early universe. At 380,000 years after the Big Bang, density variations of 1 part in 30,000 existed on all scales, imprinted by quantum fluctuations during inflation, and gravitational collapse during the radiation-dominated era. Regions with above-average density had stronger gravity, attracting surrounding matter. Over billions of years, these regions collapsed, forming the first stars and galaxies by several 100 million years after the Big Bang. By 1 to 2 billion years, galaxies had clustered into groups and early clusters. By 5 billion years, the epoch when we observed the Boss Great Wall, these clusters had assembled into superclusters and great walls through continuous infall along filaments. The discovery validates the lambda CDM cosmological model. This model predicts that structure formation proceeds hierarchically through gravitational collapse in a dark matter-dominated universe with dark energy. Computer simulations implementing lambda CDM produce cosmic webs with filaments, walls, clusters, and voids, qualitatively similar to observations. Quantitatively, the simulations predict a certain abundance of structures at different scales and epochs. The Boss Great Wall's existence, size, and epoch are consistent with lambda CDM predictions. Simulations occasionally produce structures of similar size at similar epochs. If observations found many more or many fewer great walls than predictions, it would indicate problems with the model. The agreement between observations and simulations supports the standard cosmological model. The Boss Great Wall's influence on its surroundings extends across hundreds of millions of light-years. The structure's enormous mass creates a gravitational potential well that affects galaxy motions far beyond the structure itself. Galaxies within several 100 million light-years experience gravitational pull toward the wall, contributing to large-scale flows in the cosmic velocity field. These flows are similar to the flows toward Laniakea or the Shapley supercluster. Mass concentrations influence galaxy motion across vast distances. Mapping these flows helps define basins of attraction and reveals the universe's dynamical structure. The Boss Great Wall likely defines one such basin, where galaxies within a certain region all flow toward the wall's densest parts. The structure demonstrates the cosmic web's pervasiveness. Great walls aren't rare anomalies, but regular features of cosmic structure. As surveys extend to greater volumes, more great walls are discovered. The Boss survey's larger volume, compared to earlier surveys, revealed the Boss Great Wall. Future surveys, covering even larger volumes, will discover additional walls. This suggests that the observable universe contains numerous great walls, possibly hundreds or thousands, depending on how we define and count them. Each wall represents a region where the cosmic web organized matter into large-scale sheets. The walls separate even larger voids, creating a foam-like structure where matter concentrates on void boundaries, and voids occupy most volume. Future observations will further clarify the Boss Great Wall's properties. The Dark Energy Spectroscopic Instrument, or DESI, is re-observing many regions covered by Boss with better spectroscopic resolution and deeper sensitivity. DESI will detect more galaxies in the Boss Great Wall region, improving the three-dimensional map and revealing smaller-scale structure within the wall. The Euclid Space Telescope, launched in 2023, will observe the Boss Great Wall region in infrared wavelengths, detecting additional galaxies and measuring gravitational lensing to map dark matter distribution. These observations will show whether the Boss Great Wall is a simple sheet-like structure or has complex internal structure with multiple subwalls, filaments, and voids. Understanding one of the largest structures in detail provides insights into how gravity, dark matter, and dark energy shaped the universe's largest features. The cosmic voids occupying most of space. Cosmic voids are vast, underdense regions where galaxies are sparse or absent, occupying approximately 80% of the universe's volume, while containing only 10 to 20% of its galaxies. These enormous empty bubbles in the cosmic web range from 100 million to over 2 billion light-years in diameter, dwarfing even the largest galaxy clusters. Voids aren't completely empty, but contain far fewer galaxies than average typical voids, have 10 to 20% of the galaxy density found in average regions, while some supervoids contain less than 5%. The voids formed as matter evacuated under dense regions during cosmic evolution, flowing along filaments toward overdense regions that became galaxy clusters and walls. Voids expand faster than the cosmic average because their low density generates weaker gravity, allowing dark energy's repulsive effect to dominate and accelerate expansion within void interiors. The Boötes void, discovered in 1981 by Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman during a redshift survey, was one of the first large voids identified. The void spans approximately 330 million light-years in diameter and lies about 700 million light-years from Earth, centered roughly in the direction of the constellation Boötes. The discovery came when the team measured redshifts for galaxies in this region and found a conspicuous absence of galaxies at redshifts corresponding to distances between 600 million and 900 million light-years. The region that should have contained thousands of galaxies contained only about 60, making it spectacularly underdense. The discovery surprised astronomers' previous models hadn't predicted voids this large and empty, forcing revision of structure formation theories to account for how such enormous underdense regions could form. The KBC void, named after its discoverers Ryan Keenan, Amy Barger, and Lennox Cowie, who identified it in 2013, is potentially the largest void in the nearby universe, measuring approximately 2 billion light-years in diameter. More remarkably, observations suggest the Milky Way may reside within this void or near its edge. The KBC void center lies roughly 1 billion light-years away, and galaxy density within the void is about 20% below average. If the Milky Way truly resides in a large void, this would affect cosmological measurements. Observations from within a void would show systematically different expansion rates and structure statistics than observations from average density regions. This possible location has been proposed as one explanation for tensions between local and global measurements of the Hubble constant, though this interpretation remains controversial. Void properties vary systematically with size. Small voids, 50 to 100 million light-years in diameter, are more common and have higher internal galaxy densities, perhaps 30 to 50% of average. Medium voids, 100 to 300 million light-years, are less common and more underdense, containing 10 to 20% of average galaxy density. Large voids and supervoids exceeding 300 million light-years are rare and extremely underdense, some containing fewer than 5% of average galaxy density. The largest voids approach 2 billion light-years in diameter, rivaling or exceeding the sizes of the largest walls and superclusters. This size distribution reflects how structure formation amplified initial density variations. Larger initial underdensities produced larger voids, but extremely large underdensities were rarer, making supervoids less common than smaller voids. Void shapes are approximately spherical or ellipsoidal, but show significant variation. Some voids are nearly spherical, expanding symmetrically in all directions. Others are elongated, resembling cigars or pancakes depending on how matter flowed away from the underdense region. Voids aren't isolated, they connect to each other and to filaments, creating a foam-like structure where void walls touch at filaments and walls meet at clusters. The cosmic web can be understood as either matter organized into filaments and walls, or as voids separated by thin sheets of matter. Both descriptions capture the same structure from different perspectives. The soap bubble analogy is apt. Matter concentrates in thin films surrounding air bubbles, with the bubbles being voids and the films being walls and filaments. Void interiors aren't perfectly empty. Most voids contain a few galaxies, typically small dwarf galaxies rather than large spirals or ellipticals. These void galaxies are often isolated, separated from neighbours by tens of millions of light years, making them among the loneliest galaxies in the universe. Void galaxies tend to be bluer, indicating active star formation, because they haven't undergone the interactions and mergers common in dense regions that shut down star formation. Some voids also contain small galaxy groups, clusters of a few galaxies, showing that structure exists within voids, just at much lower density than average. The galaxies within voids likely formed from rare overdensities that existed in the initially underdense regions before matter evacuated towards surrounding filaments. Voids expand at rates exceeding the cosmic average. The expansion rate is described by the Hubble parameter, which varies slightly from place to place depending on local density. In overdense regions like clusters, gravity slows expansion below the cosmic average. In some cases, gravity can overcome expansion entirely, causing clusters to contract. In underdense regions like voids, gravity is weak. Less matter means less gravitational attraction. Dark energy's repulsive effect, which is uniform across space, becomes relatively more important in low-density regions. The combination of weak gravity and constant dark energy makes voids expand about 1 to 2% faster than the cosmic average. This faster expansion further evacuates matter from void interiors, amplifying the underdensity in a runaway process. The largest voids grow by merging smaller voids. Structure formation simulations show that the early universe contained many small voids, tens of millions of light years across, that expanded and merged over time. When two expanding voids meet, the wall separating them becomes thinner as matter flows outward from both sides. Eventually, the wall contains too little matter to remain distinct, and the two voids merge into one larger void. This hierarchical merging produces the void size distribution observed today, with many small voids, fewer medium voids, and rare supervoids. The process continues. Voids are still merging, gradually creating larger, underdense regions as the universe expands and structure formation proceeds. Void abundance and size distribution test cosmological models. The lambda CDM model predicts specific statistics for how many voids of each size should exist in a given volume. Surveys measuring void sizes and abundances can test whether observations match predictions. Results show general agreement. Observed void distributions match lambda CDM simulations within uncertainties. However, some studies have claimed an excess of large voids, particularly at high redshift, which might indicate tensions in the model. The KBC void's possible enormous size also raises questions to a 2 billion light-year void is near the upper limit of what lambda CDM allows. Whether these are genuine problems or statistical flukes remains debated, requiring better observations and larger surveys to resolve. Voids affect the cosmic microwave background through the integrated Sachs-Wolf effect. Photons from the CMB, travelling from the early universe to us, pass through large-scale structures. When a photon falls into a void's gravitational potential, entering a region with below-average gravity, it gains energy, blue shifting slightly. When it climbs out of the potential, exiting the void, it loses energy, red shifting. In a static universe, These effects would cancel gain equals loss. But in an expanding universe with dark energy, voids grow deeper over time. Photons exiting a void don't climb as high a potential as they fell when entering because the void expanded, making its potential shallower. The net result is photons lose energy crossing voids, appearing slightly cooler in the CMB. The Eridanus supervoid, which will be discussed in detail in the next chapter, provides an example of void CMB connection. This 1.8 billion light-year void underlies the cold spot in the CMB, a region about 70 microkelvins colder than average. The temperature decrement matches predictions for the integrated Sachs-Wolf effect from a large void. Other voids also correlate with CMB cold spots, though the effects are small, typically only 10 to 20 microkelvins. Detecting these correlations requires careful statistical analysis, comparing void locations from galaxy surveys with CMB temperature maps from satellites like Planck. The correlations confirm that large-scale structure affects the CMB, validating our understanding of how photons interact with gravitational potentials from structures billions of light-years across. Future void studies will map voids at high redshift, probing structure formation's history. Current surveys primarily map voids at redshift Z less than 1, corresponding to the universe younger than 8 billion years old. Extending surveys to Z equals 2 or 3, when the universe was 3 to 4 billion years old, will show how voids evolved. At earlier epochs, voids were smaller and less underdense because structure formation had less time to proceed. Comparing void properties at different epochs tests structure formation models by showing how fast voids grew. The Dark Energy Spectroscopic Instrument and future surveys like those from the Nancy Grace Roman Space Telescope will map high redshift voids, revealing the universe's structure during the crucial epoch when dark energy began dominating and slowing structure formation, the Eridanus supervoid and CMB cold spot. The Eridanus supervoid is a massive, underdense region spanning approximately 1.8 billion light-years in diameter, located in the constellation Eridanus, at average distance roughly 2.5 billion light-years from Earth, corresponding to redshift Z, approximately 0.22. Discovered in 2015 by Istvan Shapudi of the Institute for Astronomy at the University of Hawaii and colleagues, the supervoid is one of the largest and most underdense structures known. The Eridanus supervoid contains about 20 to 30% fewer galaxies than average regions, an enormous deficit given its size. The supervoid's significance extends beyond its impressive dimensions. It underlies the cold spot in the cosmic microwave background, a mysterious region about 10 degrees across, where CMB temperature is approximately 70 microkelvins colder than the surrounding average temperature of 2.7255 Kelvin. The CMB cold spot was discovered in 2004 when the Wilkinson Microwave Anisotropy Probe, or WMAP, released its first full sky temperature map. The cold spot appears in the southern galactic hemisphere in the direction of Eridanus as a roughly circular region with temperature about 70 microkelvins below average. For context, typical CMB temperature fluctuations are 18 microkelvins root mean square, making the cold spot's 70 microkelvin anomaly nearly 4 times larger than typical. Statistical analysis showed the cold spot had only about 1 inch, 1,000 to 1 inch, 10,000 probability of occurring by chance in a universe described by standard cosmology. This prompted numerous explanations ranging from mundane, a statistical fluke, to exotic evidence of parallel universes colliding or topology defects from the early universe. The connection between the Eridanus supervoid and cold spot was established through multiple lines of evidence. Galaxy surveys mapping the three-dimensional distribution of galaxies found that the region of sky corresponding to the cold spot showed a deficit of galaxies at distances ranging from 1.5 billion to 3 billion light-years. The deficit formed a roughly spherical, underdense region, the supervoid. The supervoid's position aligned with the cold spot's position on the sky within observational uncertainties. The supervoid's depth, how underdense it is, and size, its diameter, matched what would be needed to produce a cold spot of the observed temperature through the integrated Sachs-Wolf effect. The coincidence of position, size, and depth strongly suggested that the supervoid causes the cold spot through gravitational effects on CMB photons. The integrated Sachs-Wolf effect, or ISW effect, explains the connection quantitatively. CMB photons, travelling from recombination 380,000 years after the Big Bang to us now 13.8 billion years later, pass through evolving gravitational potentials from large-scale structures. When photons fall into a potential well approaching an overdense region, they blue shift, gaining energy. When they climb out, they redshift, losing energy. In a matter-dominated universe where structures don't evolve, these effects cancel. Photons lose as much energy climbing out as they gain falling in. But in a dark energy-dominated universe, structures evolve as dark energy causes accelerated expansion. Voids grow deeper over time as matter continues evacuating them. Photons falling into a void gain less energy than they lose climbing out, because the void deepened while they crossed it, resulting in net energy loss. Quantitative calculations show that the Eridanus supervoid should produce a temperature decrement of approximately 10 to 20 microkelvins through the ISW effect. This is significantly less than the cold spot's observed 70 microkelvin decrement. The discrepancy means the supervoid alone can't fully explain the cold spot. Either additional effects contribute, or the cold spot has multiple causes, including the supervoid plus statistical fluctuations. Some researchers have proposed that the supervoid is aligned with additional smaller voids along the line of sight, creating a cumulative cooling effect. Others suggest the cold spot might result from primordial fluctuations in the CMB fluctuations frozen in at recombination that happen to align with the supervoid by chance. The truth might combine both explanations. Alternative explanations for the cold spot have been proposed and largely ruled out. One hypothesis suggested it resulted from a parallel universe colliding with ours during the inflationary epoch, leaving an imprint in the CMB. This idea, while provocative, lacks supporting evidence beyond the cold spot itself and requires accepting speculative multiverse theories. Another proposal suggested the cold spot is a texture, a topological defect from symmetry breaking in the early universe. Textures can create cold spots, but detailed analysis of the cold spot's temperature profile doesn't match texture predictions. A supervoid explanation, while incomplete, is more conservative and requires only known physics, gravity, dark energy, and structure formation, making it the preferred explanation despite not fully accounting for the cold spot's magnitude. The supervoid's existence raises questions about the cosmological principle. A structure 1.8 billion light-years in diameter is approaching the scale where the universe should be homogeneous. While not as extreme as the controversial Hercules Corona Borealis Great Walls claimed 10 billion light-year size, the Eridanus supervoid is nonetheless extraordinary. Statistical analysis shows that voids this large and underdense are rare but not impossible. In lambda CDM simulations, occasionally produce comparable structures. The supervoid's existence doesn't require abandoning the cosmological principle or invoking new physics, but it lies near the tail of the expected distribution. Finding multiple such supervoids might indicate a problem, but as an isolated case, it's consistent with standard cosmology. observations have mapped the supervoid structure in detail. The supervoid isn't a single empty sphere, but a complex of multiple underdense regions merged together. The largest component spans about 1.8 billion light-years, but smaller subvoids within it have diameters of 300 to 500 million light-years. The galaxy density drops gradually toward the supervoid's center, rather than dropping sharply at a boundary. The transition from average density to void interior is smooth over several hundred million light-years. This gradual transition is typical of large voids, which form from broad, underdense regions rather than being carved out of uniform backgrounds. The smooth density profile means the supervoid's edge isn't well defined. Choosing different density thresholds gives different diameters, explaining why published sizes vary between 1.5 and 2 billion light-years. The supervoid's age and formation history connect to cosmic evolution. The supervoid lies at redshift Z, approximately 0.22, meaning we observe it as it was 2.5 billion years ago when the universe was 11.3 billion years old. At that epoch, dark energy had been dominating for about 6 billion years, driving accelerated expansion. The supervoid likely began forming from a large, underdense region present in the early universe, a location with slightly below average matter density at recombination. Over billions of years, gravity amplified this underdensity as matter flowed away from the low-density region towards surrounding overdensities. By 11.3 billion years after the Big Bang, the underdensity had become a prominent void. The void continues evolving, it's still expanding faster than average and becoming more underdense, though dark energy prevents voids from becoming arbitrarily empty. The discovery utilized the Pan-STARRS 1 survey in Hawaii, combined with WISE infrared observations from NASA's Space Telescope. Pan-STARRS 1 provided optical imaging showing galaxy positions and brightnesses. WISE provided infrared observations that helped identify galaxies at specific distances. By combining these datasets with spectroscopic redshifts from other surveys, Sapudi's team constructed a three-dimensional map showing galaxy density versus position. Statistical analysis comparing observed density to simulated random distributions confirmed that the underdensity was significant, not a statistical fluke, but a genuine structure. The analysis also measured the supervoid's alignment with the cold spot and calculated the expected ISW temperature decrement, establishing the connection between void and cold spot. The Planck satellite's observations confirmed the cold spot with improved precision. Planck mapped the CMB with better angular resolution and sensitivity than WMAP, measuring temperature across the entire sky with accuracy better than 1 microkelvin. Planck confirmed the cold spot exists with temperature decrement 70 microkelvins and size roughly 10 degrees. Planck also measured CMB polarization, which provides additional information about whether temperature features result from primordial fluctuations or ISW effects. The polarization pattern around the cold spot is consistent with primordial fluctuations, suggesting the cold spot might combine primordial fluctuation with ISW effect from the supervoid. This hybrid explanation, part primordial, part supervoid, might resolve the discrepancy between the supervoid's predicted 20 microkelvin effect and the observed 70 microkelvin cold spot. Future observations will better constrain the supervoid's properties. The Dark Energy Spectroscopic Instrument is measuring redshifts for millions of galaxies, including many in the Eridanus region. These measurements will map the supervoid's structure at higher resolution, revealing internal features and better measuring its depth. The Legacy Survey of Space and Time at the Vera C. Rubin Observatory will photograph the Eridanus region repeatedly, detecting faint galaxies that previous surveys missed. These observations will show whether the supervoid is even larger and deeper than currently estimated, or whether current estimates overstate its significance. Improved measurements will also better predict the ISW effect magnitude, testing whether the supervoid truly explains the cold spot or whether additional explanations are needed. The Eridanus supervoid exemplifies how modern astronomy connects structures at vastly different scales. The CMB originates from 380,000 years after the Big Bang, when the universe was tiny and hot. The supervoid is a present-day structure spanning billions of light-years. Yet these structures connect the supervoid's gravity affects ancient photons traveling through it, creating an observable signal. This connection allows using the CMB to study large-scale structure, and using large-scale structure to interpret CMB anomalies. The interplay between early universe signals and late universe structures provides a powerful tool for testing cosmology, revealing how the universe evolved from the tiny fluctuations present at recombination to the immense structures populating the cosmos today. The Coma Cluster with 1,000 galaxies. The Coma Cluster, officially designated Abell 1656, is one of the richest and most thoroughly studied galaxy clusters in the universe. Located approximately 321 million light-years away in the constellation Coma Berenices, the cluster contains over 1,000 identified large galaxies, plus thousands of smaller dwarf galaxies within a region roughly 20 million light-years in diameter. The cluster's total mass is approximately 10 million billion, 10 to the 15th times the Sun's mass, making it one of the most massive structures in the nearby universe. The Coma Cluster played a crucial role in discovering dark matter in 1933. Astronomer Fritz Zwicky measured galaxy velocities within the cluster and found they moved too fast for the visible matter alone to hold them together, requiring unseen mass to prevent the cluster from flying apart. The cluster's discovery traces to the 18th and 19th centuries, when astronomers noticed numerous nebulae later understood as galaxies clustered in Coma Berenices. William Herschel catalogued 8 nebulae in this region in the 1,780 seconds. His son John Herschel added more in the 1,860 seconds. By the early 20th century, photographic surveys revealed dozens of galaxies concentrated in a small area. The cluster's true nature became clear in the 1,920 seconds when Edwin Hubble and others demonstrated that spiral nebulae were distant galaxies beyond the Milky Way. The concentration of hundreds of galaxies in Coma Berenices indicated a genuine physical cluster rather than a chance alignment, a bound system where galaxies orbit under mutual gravitational attraction. Fritz Zwicky's 1933 study of the Coma Cluster provided the first evidence for dark matter, though the term wasn't coined until later. Zwicky measured radial velocities, motion toward or away from Earth, for 8 galaxies in the cluster, using spectra obtained with the 100-inch Hooker telescope at Mount Wilson Observatory. The velocities ranged from nearly 7,000 kilometers per second in some directions to 0 or negative in others, indicating the galaxies were orbiting within the cluster with velocity dispersion, the spread of velocities around 1,000 kilometers per second. Zwicky applied the virial theorem, which relates kinetic energy to gravitational potential energy, to estimate the cluster's mass needed to keep such fast-moving galaxies bound. His calculations showed the cluster must contain 400 times more mass than accounted for by visible stars in the galaxies. Zwicky initially attributed the missing mass to faint stars or gas between galaxies, understandable, given that dark matter wasn't yet conceived as a fundamental component of the universe. He called the unseen material Dunkel Materie, German for dark matter, though this term wasn't widely adopted until the 1970 seconds. Subsequent observations confirm Zwicky's basic finding: the Coma cluster contains far more mass than visible. Later, measurements with more galaxies refined the velocity dispersion to about 1,000 to 1,200 kilometers per second, and the total mass to roughly 10 million billion solar masses. Of this, visible stars and galaxies account for only about 2%, 200 billion solar masses. Hot gas detected in X-rays contributes another 13%. The remaining 85% is dark matter, invisible except through gravitational effects. X-ray observations from satellites like Uhuru in the 1970 seconds, Einstein Observatory in the 1980 seconds, and later Chandra and XMM Newton revealed that the Coma cluster contains enormous quantities of hot gas. The gas temperature reaches approximately 90 million Kelvin, hot enough that electrons are stripped from atoms, and the gas emits X-rays through thermal Bremsstrahlung radiation. This gas fills the space between galaxies, making up what's called the intracluster medium. The gas mass is several trillion solar masses, far exceeding the stellar mass in galaxies, but still much less than the dark matter mass. The gas temperature indicates the depth of the gravitational potential, while hotter gas requires deeper potential, confirming the cluster's enormous mass inferred from galaxy velocities. The Coma cluster's galaxy population shows distinct features. The cluster is dominated by elliptical galaxies rather than spiral galaxies. The two brightest cluster galaxies, NGC 4874 and NGC 4889, are giant ellipticals near the cluster's center, each containing over 1 trillion stars. These galaxies are more massive than the Milky Way by factors of 10 or more. Their dominance reflects the cluster environment in dense clusters. Galaxies frequently collide and merge, building larger ellipticals while disrupting spirals. Galaxy collisions at velocities exceeding 1,000 kilometers per second can strip gas from galaxies through ram pressure, the resistance from colliding with intracluster gas. Stripped of gas, galaxies can't form new stars, explaining why cluster galaxies tend to be red ellipticals dominated by old stars rather than blue spirals with active star formation. The cluster's large-scale structure includes substructure. The cluster isn't a smooth distribution, but shows clumps and groups. Observations reveal at least 2 major subclusters that merged sometime in the past billion years. The merger is evidenced by the galaxy distribution showing 2 concentration peaks, and by X-ray observations showing disturbances in the hot gas distribution. When subclusters merge, their galaxies pass through each other, relatively unscathed. The space between stars within galaxies is so vast that direct stellar collisions are rare, but the gas collides, heating and compressing, creating shock waves visible in X-ray images. The Coma cluster's merger history explains some of its observed properties, including slight asymmetry in galaxy and gas distributions and the high temperature of the intracluster gas. The cluster's distance is well established through multiple methods. Early estimates used galaxy luminosities, assuming cluster galaxies have similar intrinsic brightness to nearby galaxies of known distance. More precise measurements came from the Tully-Fisher relation, which relates spiral galaxy luminosity to rotation velocity, and the fundamental plane relation for elliptical galaxies, which relates size, surface brightness, and velocity dispersion. These methods give consistent distances around 320 to 330 million light-years. The cluster's redshift is Z equals 0.0231, corresponding to recession velocity 6,000 900 kilometers per second due to cosmic expansion. This distance places the Coma cluster well within the local universe, close enough for detailed study of individual galaxies, but far enough to represent a massive, mature cluster. The cluster's role in cosmology extends beyond dark matter discovery. The Coma cluster serves as a standard for defining rich clusters with 1,000 or more large galaxies. Astronomers classify clusters by richness, with Coma being richness class 2 inches the Abell catalogue, extremely rich, but not the very richest. The cluster's properties size, mass, galaxy content, gas temperature are typical of massive clusters, making it a benchmark for comparing with clusters at greater distances. Observing how cluster properties change with distance equivalently, with look-back time, reveals how clusters evolve, testing structure formation models. Coma represents the endpoint of cluster evolution, a fully formed, relaxed cluster with well-mixed galaxies and gas. Gravitational lensing by the Coma cluster has been detected but is relatively weak compared to more distant clusters. Gravitational lensing occurs when light from background galaxies is bent by the cluster's gravity, distorting their images into arcs or multiple images. The lensing effect's strength depends on cluster, mass, and geometry. More massive clusters and optimal alignment produce stronger lensing. Coma's relatively low redshift means fewer background galaxies lie behind it, and those that do are at relatively small distances beyond the cluster, limiting lensing strength. Nonetheless, weak gravitational lensing, subtle distortions of many background galaxy shapes, has been measured around Coma. The lensing signal maps the cluster's total mass distribution, providing an independent mass measurement that agrees with mass from galaxy velocities and X-ray gas, confirming the cluster's enormous mass and dark matter content. The Coma cluster's future evolution will see it continuing to accrete matter from surroundings. Small galaxy groups falling into the cluster along filaments will add mass and galaxies over time. The cluster may merge with neighbouring clusters if they're close enough and moving slowly enough. However, dark energy's acceleration limits growth structures beyond certain scales won't collapse. The Coma cluster's 20 million light-year size is well below this limit, so the cluster will remain bound and continue accreting matter. In tens of billions of years, galaxies within the cluster will likely merge further, building even larger central galaxies. The cluster's hot gas may cool and form new stars, or be expelled by active galactic nuclei, supermassive black holes in central galaxies that eject gas through powerful jets. Understanding these processes requires simulating cluster evolution, an active area of research. The Coma cluster represents the universe's structure on one of its largest scales, the cluster scale of tens of millions of light-years. Clusters sit at the nodes of the cosmic web where filaments converge. They represent the most overdense regions, where matter accumulated most successfully. Studying clusters reveals how gravity, dark matter, and dark energy shape structure. The Coma cluster, being nearby and extensively observed, provides the best laboratory for studying cluster physics. Lessons learned from Coma apply to understanding distant clusters observed as they were billions of years ago, helping reconstruct structure formation's history. From Zwicky's pioneering observations 90 years ago to modern X-ray and lensing studies, the Coma cluster continues teaching us about the universe's largest gravitationally bound structures, the Perseus-Pisces supercluster chain. The Perseus-Pisces supercluster is a massive chain of galaxy clusters and superclusters extending across approximately 1 billion light-years, forming one of the largest structures in the nearby universe. This elongated structure connects multiple rich galaxy clusters, including the Perseus cluster, the Pisces-Cetus supercluster, and numerous smaller clusters and groups into a coherent, filamentary complex. The Perseus-Pisces chain lies at distances ranging from 200 to 600 million light-years from Earth, making it one of the nearest examples of supercluster scale structure. The total mass of the entire chain is estimated at hundreds of millions of billions of solar masses, though determining precise values is difficult because the structure isn't a single bound system but rather a series of connected overdensities embedded in the cosmic web. The Perseus cluster, officially Abell 426, forms one major node in the chain, located 240 million light-years away in the constellation Perseus. This cluster contains over 500 large galaxies within a 1-5 million light-year region. The cluster's total mass is approximately 1 quadrillion solar masses, comparable to the Coma cluster. The Perseus cluster is notable for its X-ray emission. It's one of the brightest X-ray sources in the sky outside our galaxy. X-ray observations reveal hot gas at temperatures around 50 million Kelvin, filling the cluster's interior. The cluster's central galaxy, Perseus A, or NGC 1275, hosts an active supermassive black hole that drives jets of relativistic particles into the surrounding gas, creating massive bubbles and ripples visible in X-ray images, evidence of feedback processes where black holes affect their host clusters. The Pisces-Cetus supercluster, lying in the opposite direction from Perseus at distances around 500 to 600 million light-years, forms another major component. This supercluster contains dozens of galaxy clusters and groups spread across a region roughly 300 million light-years across. The supercluster includes numerous Abell clusters, rich clusters catalogued by George Abell in the 1950 seconds based on their high galaxy densities. The Pisces-Cetus region shows clear filamentary structure. Galaxies aren't uniformly distributed, but concentrate along elongated filaments connecting denser cluster regions. The supercluster represents a partially collapsed structure where gravitational attraction has pulled galaxies together but hasn't yet assembled everything into a single massive cluster. The connection between Perseus and Pisces-Cetus forms through intermediate structures. Galaxy surveys reveal continuous overdensities, regions with above-average galaxy density linking the two ends. These overdensities include smaller galaxy groups and clusters at intermediate distances between 300 and 500 million light-years. The structure resembles a chain with major clusters as large beads and smaller groups as connecting links. Mapping the three-dimensional galaxy distribution shows that this chain isn't just a projection effect. The galaxies physically align in 3 dimensions, forming a genuine, elongated structure. The chain likely formed along a primordial filament, a region with elongated overdensity present in the early universe that collapsed into its current configuration over billions of years. The Perseus-Pisces chain is part of the larger Pisces-Cetus supercluster complex, which extends even farther. This complex includes additional superclusters beyond Pisces-Cetus, creating a structure that may extend 1.5 billion light-years or more, depending on how boundaries are defined. The complex connects to other large-scale structures, including potential connections to Laniakea through filaments. Precisely mapping these connections requires extensive redshift surveys covering large areas of sky with good depth, surveying many galaxies at distances reaching 1 billion light-years. As surveys improve, the connectivity of large-scale structures becomes clearer, revealing how the cosmic web links structures across the universe. The mass-to-light ratio in the Perseus-Pisces chain reveals dark matter's dominance. Counting galaxies and estimating stellar mass from their luminosity gives the visible mass roughly 1 trillion solar masses for major clusters like Perseus. Measuring galaxy velocities and applying the virial theorem, gives dynamical mass the total mass needed to keep fast-moving galaxies bound. For Perseus and similar clusters, dynamical mass exceeds visible mass by factors of 50 to 100, indicating that 98 to 99% of mass is dark matter and gas rather than stars. X-ray observations show that hot gas contributes 10 to 15% of total mass, leaving 85 to 88% as dark matter. This dark matter fraction is typical of galaxy clusters and confirms that dark matter dominates gravitational interactions on cluster scales. The chain's formation history can be reconstructed through observations and simulations. The Perseus-Pisces overdensity originated from density fluctuations in the early universe regions with slightly above average density at recombination. Over billions of years, gravity amplified these fluctuations. Matter flowed along filaments toward the overdense regions, accumulating into clusters. Smaller structures collapsed first by 1 billion years after the Big Bang. The first galaxies had formed. By 3 to 5 billion years, galaxy groups had assembled. By 8 to 10 billion years, rich clusters like Perseus had formed. The process continues. Clusters still accrete matter from surroundings, growing in mass over time. The Perseus-Pisces chain represents structure at an intermediate stage. Clusters have formed but haven't merged into a single supercluster. Velocity flows in the Perseus-Pisces region show that galaxies move toward cluster centers along filaments. These flows, called peculiar velocities, reflect gravitational attraction to massive clusters. Galaxies within a few tens of millions of light-years of Perseus are falling toward it at hundreds of kilometers per second. Galaxies along the filament connecting Perseus to Pisces Cetus show velocity patterns indicating they're streaming along the filament. These velocity flows define basins of attraction regions where galaxies share common gravitational influence. The Perseus cluster defines one basin. The Pisces Cetus supercluster defines another. The filament connecting them marks a transition region where flows converge toward both attractors. The Perseus cluster's central galaxy exhibits dramatic feedback effects. NGC 1275 hosts a supermassive black hole with mass approximately 340 million times the Sun's mass. Gas falling toward the black hole forms an accretion disk where gravitational energy converts to heat and radiation. Some material doesn't fall in but is ejected in powerful jets moving at nearly light speed. These jets inflate enormous bubbles in the surrounding hot gas, visible in Chandra X-ray images as cavities reaching hundreds of thousands of light-years across. The bubbles displace gas, creating pressure waves, essentially sound waves that ripple through the cluster. These sound waves have wavelengths of thousands of light-years and periods of tens of millions of years, making them the deepest notes in the universe, 57 octaves below middle C. The supercluster chain's orientation may affect local cosmic flows. The Perseus-Pisces structure extends roughly perpendicular to the direction of the Great Attractor and Shapley supercluster. This geometry suggests that the local group's motion results from attraction toward multiple large-scale structures in different directions. Perseus-Pisces might contribute 50 to 100 kilometers per second to our velocity, though this contribution is smaller than effects from closer structures like Virgo or more massive distant structures like Shapley. Disentangling individual contributions requires careful modelling of the gravitational field from all structures within several hundred million light-years, a challenging problem requiring detailed knowledge of mass distributions. Future observations will better define the Perseus-Pisces structure's extent and mass. The ongoing E-Rosetta X-ray survey is mapping hot gas in thousands of galaxy clusters across the entire sky, revealing clusters' positions and masses. Combined with optical and infrared surveys mapping galaxy positions, this will create a three-dimensional map showing how clusters connect through filaments. The Dark Energy Spectroscopic Instruments spectroscopic survey will measure redshifts for tens of millions of galaxies, including many in the Perseus-Pisces region, mapping structure with unprecedented detail. These observations will show whether the Perseus-Pisces chain is a single coherent structure or multiple structures that happen to align, and whether it connects to even larger structures at greater distances. The Perseus-Pisces supercluster chain exemplifies the cosmic web's hierarchical organization. Individual galaxies cluster into groups, groups cluster into clusters. Clusters connect along filaments, and filaments link into supercluster chains that can extend across billions of light years. Each level reflects gravitational collapse, amplifying initial density fluctuations over cosmic time. The Perseus-Pisces chain shows structure at the upper end of this hierarchy, one of the largest coherent structures that has assembled. Understanding such structures reveals the universe's organization on the largest scales where gravitational collapse operates. Beyond these scales, the universe becomes homogeneous. The transition from structured to homogeneous marks the limit where local gravitational attraction yields to cosmic expansion driven by dark energy. The large quasar groups, billions of light years across. Large quasar groups, or LQGs, are immense structures formed by clusters of quasars spanning billions of light years. Quasars are the brilliant cores of active galaxies powered by supermassive black holes, accreting matter at prodigious rates, emitting radiation visible across the universe. Because quasars are extremely luminous, they can be detected at enormous distances where normal galaxies are too faint to see, making them useful tracers of matter distribution in the distant universe. The Huge Large Quasar Group, or Huge LQG, discovered in 2013, spans approximately 4 billion light-years across, making it one of the largest structures ever detected. If confirmed as a genuine physical structure rather than a statistical artifact, the Huge LQG challenges the cosmological principle by introducing inhomogeneity on scales where the universe should be homogeneous. The Huge LQG discovery came from Roger Clowes and colleagues at the University of Central Lancashire, who analysed quasar positions and redshifts from the Sloan Digital Sky Survey's Data Release 7. The team examined 73 quasars at average redshift Z, approximately 1.27, corresponding to distance around 9 billion light-years, and look-back time to when the universe was only 4.8 billion years old, 35% of its current age. Statistical analysis showed these quasars clustered more tightly than expected by chance. The clustering occupied a region of sky about 10 degrees across at a consistent redshift range, indicating a physical structure rather than random alignment. Converting angular size and redshift to physical dimensions gave length approximately 4 billion light-years, width 1.6 billion light-years, and thickness around 1 billion light-years, an enormous ellipsoidal structure. The structure's size violates a theoretical limit called the homogeneity scale. The cosmological principle suggests the universe becomes homogeneous on scales above 300 to 400 million light-years beyond this scale. Matter distribution should be uniform on average. Some theorists have proposed stricter limits around 1.2 billion light-years based on mathematical considerations from general relativity. The Huge LQG's 4 billion light-year length exceeds these limits by factors of 3 to 10, potentially indicating problems with the cosmological principle or our understanding of structure formation. However, interpreting the structure's significance depends on whether it represents a single bound or coherent system, or merely a statistical overdensity. a region with more quasars than average, but not necessarily a physically meaningful structure. The Claus-Campusano Large Quasar Group, discovered in 1991 by Roger Claus and Louis Campusano, was one of the first large quasar groups identified. This structure contains 18 quasars at redshift Z, approximately 1.3, spanning about 2 billion light-years. Like the huge LQG, the Claus-Campusano LQG raised questions about structure size limits. Subsequent analyses have debated whether these quasar groups represent genuine structures or artifacts of statistical analysis. The challenge is that quasars are rare. Only a small fraction of galaxies host bright quasars, and observations detect only the brightest examples. With limited samples, determining whether clustering is statistically significant requires careful analysis accounting for selection effects and the multiple comparisons problem, where searching many regions increases the probability of finding apparent clusters. By chance, quasars trace underlying matter distribution because they form in massive galaxies located in overdense regions. A quasar's black hole typically has mass between 100 million and 10 billion solar masses, requiring a massive galaxy to host it. Massive galaxies preferentially form in high-density environments where gas can accumulate efficiently. Additionally, quasar activity, the phase when black holes accrete gas rapidly and shine brightly, may be triggered by galaxy interactions and mergers, which occur more frequently in dense environments. Thus, finding a group of quasars at similar redshifts suggests an underlying overdensity of galaxies, a forming supercluster or large-scale structure. The quasars mark the densest nodes within a larger matter concentration that includes many non-active galaxies, too faint to detect at these distances. The statistical significance of large quasar groups remains debated. The original huge LQG paper reported significance at the 4 sigma level, roughly 1 inch, 15,000 probability of occurring by chance. Subsequent analyses by skeptics have questioned this significance, arguing that when properly accounting for how many regions were searched and what clustering criteria were used, the true significance might be lower, perhaps 2 to 3 sigma, not sufficient for a confident detection. The debate mirrors controversies surrounding other claimed large structures, like the Hercules Corona Borealis Great Wall. With limited data and complex statistical analysis, distinguishing real structures from statistical fluctuations is challenging. Different analysis methods and assumptions can yield different conclusions about whether a structure is real. Galaxy surveys have attempted to confirm large quasar groups by searching for galaxy overdensities at the same locations and redshifts. Detecting associated galaxies would strengthen the case that quasar groups trace real structures. However, at redshifts Z equals 1 to 2, normal galaxies are faint, apparent magnitudes around 24 to 26, requiring deep imaging and spectroscopy to detect. Surveys like the Cosmos Field and GOODS have mapped galaxies in limited areas of sky to these depths. Some studies have found galaxy overdensities associated with large quasar groups supporting their reality. Other studies have found weaker or no associations. The mixed results reflect both the difficulty of observations and genuine uncertainty about whether all claimed quasar groups represent physical structures. Theoretical models predict that structures as large as 4 billion light-years shouldn't exist at redshift Z equals 1.27. At this epoch, the universe was still matter-dominated. Dark energy had begun accelerating expansion, but hadn't yet dominated. Structure formation simulations show that the largest structures at Z equals 1.27 should span around 1 to 1.5 billion light-years, comparable to today's largest superclusters. Structures 4 billion light-years across would require unusually large initial density fluctuations, larger than the cosmic microwave background allows, or would need more time to form than available. If the huge LQG is real and genuinely 4 billion light-years across, it might indicate that structure formation proceeded faster than models predict, potentially requiring revisions to lambda CDM cosmology. Alternative interpretations suggest the huge LQG might be a projection effect. The structure's elongated shape, 4 billion light-years long but only 1 billion light-years thick, hints at possible projection. The quasars might belong to multiple smaller structures at slightly different redshifts that happen to align along our line of sight. Redshift uncertainties for individual quasars are typically several hundred kilometers per second, corresponding to 10 to 20 million light-years in distance. If the structure contains subcomponents separated by these distances in the radial direction, they would appear as a single structure in redshift space. Confirming or ruling out projection requires precise redshift measurements for all member quasars, which is challenging for faint distant objects. Other large quasar groups have been identified at various redshifts. The U-1 27 LQG spans about 3 billion light-years at redshift, Z equals 1.27, slightly smaller than the huge LQG but still extraordinarily large. The U-1 11 structure spans 2.5 billion light-years at Z equals 1.11. Each discovery prompted similar debates about significance and reality. The accumulation of multiple claimed large structures at high redshift suggests either that such structures are more common than theoretical models predict, implying models need revision, or that the claimed structures include some false positives where statistical artifacts or projection effects were misidentified as genuine structures. Resolving this requires better observations, larger quasar samples, and more sophisticated statistical methods. The future of large quasar group studies depends on larger surveys. The Dark Energy Spectroscopic Instrument is observing millions of quasars across a wide range of redshifts, providing samples 10 to 100 times larger than previous studies. With larger samples, statistical tests become more powerful. Genuine structures will stand out clearly while artifacts disappear. DESI will also map galaxies at redshifts, where large quasar groups have been claimed, showing whether galaxy distributions confirm quasar clustering the Vera C. Rubin Observatory's Legacy Survey will discover many more quasars through deep imaging, feeding into spectroscopic follow-up. Within the next decade, the debate over large quasar groups should resolve either confirming their real and challenging cosmology, or showing their artifacts, vindicating standard models. Large quasar groups illustrate challenges in studying the distant universe's structure. At redshifts beyond Z equals 1, observing structure becomes difficult. Galaxies are faint, requiring long exposures and large telescopes. Quasars, being bright, are easier to detect, but are rare and might not trace structure the same way galaxies do. Additionally, at high redshift, we observe the universe when it was younger, structures were smaller and less evolved. Comparing high redshift and low redshift structure tests structure formation models by showing how structures grew over time. If large quasar groups prove real, they provide snapshots of structure in the early universe that can be compared with theoretical predictions. If they're artifacts, they teach us about analysis pitfalls in sparse datasets. Either way, the controversy drives improved observations and methods, advancing our understanding. The giant void in Eridanus at 3 billion light-years. The giant void in Eridanus is another underdense region in the constellation Eridanus, distinct from but related to the Eridanus supervoid discussed earlier. This void spans approximately 1 billion light-years in diameter and lies at distance around 3 billion light-years from Earth. The void's existence was inferred from galaxy surveys showing a deficit of galaxies in this region of sky at the corresponding redshift range. Like the Eridanus supervoid, this void has been proposed as a potential explanation for cosmic microwave background anomalies, particularly the cold spot. The void's large size and depth, how underdense it is, make it one of the most prominent underdense regions known. However, distinguishing between multiple voids along the same line of sight and determining whether they form connected structures or separate entities remains challenging. The distinction between the Eridanus supervoid at 2.5 billion light-years and this larger void at 3 billion light-years is important but sometimes confused in literature. Some analyses treat them as a single, extended, underdense region, a large void complex spanning 2 to 3.5 billion light-years distance. Others treat them as separate voids that happen to align along the same line of sight. The alignment along the direction toward the CMB cold spot isn't coincidental. Both voids contribute to the cold spot through the integrated Sachs-Wolf effect. Multiple voids along a line of sight can have cumulative effects, with each void contributing temperature decrements that add together. This stacking effect might help explain why the cold spot is colder than a single void can produce. Mapping voids at distances of 3 billion light-years requires extensive redshift surveys. The galaxies defining void boundaries lie at redshifts Z approximately 0.3 to 0.4, corresponding to distances 3 to 4 billion light-years. At these distances, galaxies appear faint apparent magnitudes, around 19 to 21, requiring moderately large telescopes for spectroscopy. Surveys like SDSS, 2DFGRS, and 6DFGS have measured redshifts for hundreds of thousands of galaxies in this redshift range, creating three-dimensional maps revealing void locations and sizes. The giant void in Eridanus appears in these maps as a region with significantly fewer galaxies than surrounding regions, typically 30 to 50% below average galaxy density. The void's shape is approximately ellipsoidal, elongated along the line of sight, the direction from Earth toward the constellation Eridanus. This elongation might be intrinsic voids, can have various shapes depending on how matter evacuated them, or might partially result from projection effects or redshift space distortions. Redshift space distortions occur because galaxy velocities contain both cosmic expansion and peculiar velocities from gravitational attraction to nearby structures. Peculiar velocities can make structures appear elongated or compressed along the line of sight in redshift space compared to their true shapes in real space. Correcting for these distortions requires models of velocity fields, adding uncertainty to void shape measurements. The void's effect on the cosmic microwave background through the integrated Sachs-Wolf effect adds to the effect from the nearby Eridanus supervoid. Calculations suggest that a 1 billion light-year void at 3 billion light-years distance produces a temperature decrement of approximately 5 to 10 microkelvins. Combined with the 10 to 20 microkelvins from the Eridanus supervoid at 2.5 billion light-years, the total effect might reach 15 to 30 microkelvins. This is still less than the cold spot's 70 microkelvin decrement, indicating additional contributions, either more structures along the line of sight or primordial fluctuations from the early universe contributing to the cold spot. The uncertainty in ISW effect calculations, which depend on void, depth, size, and dark energy properties, means the predictions have 50 to 100% uncertainties. Dark energy's properties affect the integrated Sachs-Wolf effect's magnitude. The effect depends on how gravitational potentials evolve over time, which depends on how dark energy's density and pressure change as the universe expands. If dark energy is a cosmological constant with equation of state W equals -1, potentials evolve at a specific rate, producing specific ISW signals. If dark energy is dynamical with W, varying with time, potentials evolve differently, producing different ISW signals. By measuring ISW effects from many voids and comparing with predictions for different dark energy models, astronomers can constrain dark energy's properties. The giant void in Eridanus and other large voids serve as natural laboratories for testing dark energy models through their CMB signatures. The void's age corresponds to observing it when the universe was approximately 11 billion years old at redshift Z, approximately 0.35. At this epoch, dark energy had been dominating cosmic expansion for about 5 billion years. Structure formation was slowing as dark energy's acceleration counteracted gravitational collapse. The void formed from an initially underdense region that evacuated matter over billions of years as surrounding overdensities pulled matter away. By 11 billion years after the Big Bang, the void had reached its current size and depth. The void continues evolving. It expands faster than the cosmic average and becomes progressively more underdense, though dark energy prevents it from becoming completely empty. In billions of years, the void will be larger and more underdense than we observe it today. Comparing the giant void with other large voids reveals common features. Most large voids are elongated rather than spherical, with typical axis ratios around 2:1 to 3:1. Voids aren't isolated but connect to each other and to filaments, creating the cosmic web's foam-like topology. Void interiors aren't perfectly empty. They contain a few galaxies, typically small and star-forming, surviving as isolated objects in underdense regions. Void galaxies provide insights into galaxy formation in low-density environments, without interactions and mergers common in dense regions. Void galaxies evolve differently, remaining gas-rich and blue with ongoing star formation. Studying void galaxies reveals how environment affects galaxy evolution. The void's discovery and characterization utilized multiple survey datasets. The 2DF Galaxy Redshift Survey, conducted from 1997 to 2003 using the Anglo-Australian telescope, measured redshifts for 220,000 galaxies covering large areas of southern sky, including Eridanus. The 6DF Galaxy Survey, conducted from 2001 to 2006, added 125,000 redshifts for nearby galaxies. The Sloan Digital Sky Survey covered northern sky regions including parts of Eridanus. Combining these datasets created a three-dimensional map covering redshifts from Z equals 0 to 0.5, revealing void structures, including the giant void. The survey's complementary sky coverage allowed mapping large-scale structures across both hemispheres, showing voids' global distribution. Theoretical models of void formation show that voids originate from underdense regions in the primordial density field. At recombination 380,000 years after the Big Bang, density fluctuations existed on all scales. Overdense regions became clusters and filaments. Underdense regions became voids. The initial underdensity didn't need to be large, only a few percent below average. Over billions of years, gravitational instability amplified the contrast. Matter flowed from underdense to overdense regions along gravitational gradients. The evacuation accelerated as overdense regions grew denser and exerted stronger pull. By several billion years after the Big Bang, distinct voids had formed. The process continues. Voids are still expanding and merging, creating progressively larger, underdense regions. The giant void's statistical significance has been evaluated using multiple methods. One approach compares the observed galaxy deficit with expectations from random distributions. How often would such a deficit occur by chance? Another approach uses n-body simulations of structure formation to see how often voids of similar size and depth form in models. Results show that voids as large as 1 billion light-years and as underdense as 30 to 50% below average are rare, but, expected in lambda CDM, they occur roughly once per several billion cubic light-years. Given that observable universe contains tens of billions of cubic light-years, finding a few such voids is consistent with predictions. The giant void is rare, but not impossibly rare, supporting standard cosmology. Future observations will better characterize the giant void's properties and its relationship to the CMB cold spot. The Dark Energy Spectroscopic Instrument's observations will detect more galaxies in the Eridanus region, improving three-dimensional mapping of void structure, the Vera C. Rubin Observatory's imaging will reveal faint galaxies that previous surveys missed, showing whether the void is as empty as current data suggests or contains more galaxies than detected. Improved CMB observations from missions like the proposed CMB-S4 will map the cold spot with better precision, potentially revealing substructure or features that constrain theoretical models. Combining improved void maps with improved CMB data will test whether voids fully explain the cold spot or whether additional explanations are needed. The dark matter filaments connecting clusters. Dark matter filaments form the cosmic web's backbone, connecting galaxy clusters across hundreds of millions of light-years. These thread-like structures contain approximately 60% of the universe's matter, both dark matter and ordinary matter, stretched along the intersections of primordial density fluctuations. A typical filament extends 150 to 300 million light-years in length, with width 20 to 30 million light-years, roughly 10 times longer than wide. Dark matter, comprising 85% of matter, provides the gravitational framework that shapes filaments. Ordinary matter gas and galaxies follows the dark matter distribution, accumulating in filaments where it forms stars and galaxies. Filaments are difficult to observe directly because dark matter doesn't emit light, and the gas in filaments is diffuse and hot, 100,000 to 10 million Kelvin, emitting faint X-rays and ultraviolet light that requires sensitive instruments to detect. The first direct detections of dark matter filaments came through gravitational lensing observations. Gravitational lensing occurs when light from distant galaxies passes through intervening matter, both dark matter and ordinary matter, and is bent by gravity, distorting the background galaxy's images into arcs or changing their apparent shapes. Strong lensing by massive galaxy clusters produces dramatic arcs and multiple images. Weak lensing produces subtle shape distortions. Galaxies appear slightly elongated perpendicular to the mass concentration direction. By measuring shape distortions for many background galaxies across large areas of sky, astronomers can map the foreground mass distribution, revealing dark matter's location even though it's invisible. Early weak lensing maps from the 2000s revealed mass concentrations at galaxy cluster locations, confirming dark matter's presence. In 2012, a team led by Jörg Dietrich at the University Observatory Munich announced the first convincing detection of a dark matter filament connecting two galaxy clusters. The filament bridges Abell 222 and Abell 223, two clusters separated by roughly 30 million light-years at distance approximately 2.2 billion light-years from Earth. The team combined weak gravitational lensing data showing mass distribution with X-ray observations showing hot gas and optical observations showing galaxy positions. All three components, aligned dark matter, formed a bridge between clusters detected through lensing. Hot gas filled the bridge detected through X-rays, and galaxies within the bridge followed the dark matter and gas distribution. The convergence of evidence from multiple wavelengths confirmed the filament's reality and demonstrated that filaments contain substantial amounts of both dark and ordinary matter. The warm-hot intergalactic medium, or WIM, fills dark matter filaments with diffuse gas at temperatures between 100,000 and 10 million Kelvin. This gas comprises roughly half of the universe's ordinary matter, the so-called missing baryons that weren't accounted for in galaxies, stars, or cold intergalactic gas. The WIM forms when gas falls into filaments' gravitational potential wells. As gas accelerates toward filaments, it gains kinetic energy. When gas streams from different directions collide within filaments, collisions convert kinetic energy to thermal energy, heat raising gas temperature to hundreds of thousands or millions of Kelvin. At these temperatures, hydrogen is ionized electrons are stripped from protons, making the gas emit primarily in ultraviolet and X-ray wavelengths rather than visible light. This emission is faint. The gas is so diffuse that total luminosity is low despite enormous volume. Detecting WIM requires sensitive X-ray and ultraviolet observations. X-ray satellites like XMM Newton and Chandra have searched for emission from filaments, detecting signals in some cases, but often finding emission too faint for definitive detection. Ultraviolet observations looking for absorption lines in spectra of distant quasars, where intervening WIM gas absorbs specific wavelengths corresponding to oxygen, carbon, or nitrogen ions, have provided more detections. The Cosmic Origin Spectrograph on the Hubble Space Telescope has detected oxygen absorption lines indicating gas at temperatures around 300,000 Kelvin along lines of sight passing through filaments. The absorption occurs at redshifts matching filament distances, confirming the gas lies within filaments rather than elsewhere along the line of sight. Filament widths are determined by the gravitational potential depth and gas pressure. Dark matter collapses into thin filaments widths only 10 to 20 million light-years because it's collisionless. Dark matter particles pass through each other without interacting, allowing them to settle into narrow distributions along potential minimums. Ordinary matter, being collisional, gas atoms collide. Exchanging energy can't collapse as thinly. Gas pressure supports gas against complete collapse, limiting filament widths. The balance between gravitational compression pulling gas into filaments and pressure pushing outward determines equilibrium width. For typical filament masses and temperatures, this equilibrium occurs at widths around 20 to 30 million light-years, consistent with observations of galaxy distributions along filaments. The Cosmic Web Imager, an instrument built by Christopher Martin and colleagues at Caltech, made breakthrough observations of filament gas in 2014. The instrument detected hydrogen emission from gas in a filament connecting two quasar host galaxies at redshift Z equals 2.3, distance approximately 10 billion light-years. The observations showed glowing hydrogen gas filling a region hundreds of thousands of light-years across between the galaxies. The gas wasn't as hot as WIM, only 10,000 to 100,000 Kelvin, representing cooler gas falling toward the filament from surrounding voids. The observations demonstrated that filaments contain gas at multiple temperatures, cold gas condensing from voids, warm gas in the process of heating as it falls in, and hot WHIM gas filling the filament interior. Simulations of cosmic structure formation show filament formation in detail. N-body simulations follow billions of dark matter particles under gravity, showing how initially smooth dark matter distribution fragments into filaments, walls, and halos. Hydrodynamic simulations add gas physics, heating, cooling, pressure, showing how ordinary matter follows dark matter into filaments and clusters. The simulations reproduce observed filament properties, lengths, widths, orientations, and connectivity, validating theoretical understanding of structure formation. Simulations also predict filament evolution. Filaments grow thicker and denser over time as more matter accretes, and dark energy increasingly prevents new filament formation as it dominates expansion. Future filaments will differ from present filaments. The epoch of active filament formation ended billions of years ago. The filamentary structure's topology, how filaments connect, affects structure formation efficiency. Regions where multiple filaments converge become sites for cluster formation because matter flows along filaments toward intersections. Clusters sit at nodes where 3, 4, or more filaments meet. The number of filaments meeting at a node affects cluster properties. Clusters at major intersections are larger and richer than clusters at minor nodes. Filament thickness also matters. Thicker filaments contain more mass, feeding more material to clusters they connect. Understanding topology requires three-dimensional mapping of structure across large volumes, which surveys like SDSS, BOSS, and DESI provide. Statistical analysis of filament networks tests structure formation models by comparing observed topology with simulation predictions. Dark matter filament mass distribution follows a characteristic profile. Density peaks at the filament center and decreases toward edges. The profile isn't sharply defined. Filaments gradually transition into surrounding voids without clear boundaries. Defining where a filament ends and a void begins is somewhat arbitrary, depending on what density threshold is chosen. This ambiguity affects filament mass estimates. Different thresholds give different masses. Typical filaments contain masses ranging from hundreds of billions to trillions of solar masses, comparable to or exceeding galaxy cluster masses. The distributed mass along hundreds of millions of light years means filaments are less dense than clusters. Cluster density exceeds filament density by factors of 100 to 1000, but filaments' enormous volume makes their total mass contribution significant. Future observations will map dark matter filaments with increasing precision. The Euclid space mission, launched in 2023, will measure weak gravitational lensing for billions of galaxies across 1/3 of the sky. The resulting mass maps will reveal dark matter filaments connecting clusters across cosmic web. Euclid's infrared imaging will also detect galaxies in filaments, showing how galaxy formation proceeds in intermediate density environments between clusters and voids. The Vera C, Rubin Observatory's legacy survey, will provide complementary data from ground-based observations. Next-generation X-ray observatories like X-RISM and Athena, plus potential future ultraviolet missions, will detect WIM emission and absorption, measuring filament gas properties directly. These observations will test structure formation models by comparing observed filament properties, mass, width, temperature, gas, content, with theoretical predictions. Dark matter filaments represent the universe's largest organized structures below the scale where cosmic homogeneity dominates. The transition from filamentary structure to homogeneity occurs around 300 to 500 million light-years above this scale. The universe appears uniform on average, despite individual filaments extending far beyond. Understanding this transition scale tests cosmological models and the cosmological principle. The filaments themselves encode the universe's initial conditions, their sizes, orientations, and mass distributions reflect the density fluctuations present at recombination amplified by 13.8 billion years of gravitational growth. Mapping filaments across cosmic time from high redshift to present reveals structure formation's history, showing how the cosmic web assembled from initial perturbations to the intricate network we observe today. The gravity and dark matter building structures. Gravity is the fundamental force driving cosmic structure formation, amplifying tiny density variations present in the early universe into the massive structures we observe today. Dark matter, comprising 85% of the universe's matter, dominates gravitational interactions on large scales because it doesn't interact electromagnetically. It doesn't radiate, absorb, or scatter light, allowing it to collapse without energy loss. This makes dark matter the scaffold upon which visible structures form. Ordinary matter, gas and stars, follows dark matter's gravitational pull, falling into dark matter halos and filaments where galaxies and clusters assemble. The process began when the universe was only 380,000 years old, when tiny density fluctuations of 1 part in 30,000 existed. Over 13.8 billion years, gravity amplified these fluctuations by factors exceeding 100,000, creating regions where density is 100 times or more above average in clusters and 50% below average in voids. The lambda CDM model, lambda cold dark matter, provides the theoretical framework explaining structure formation. Lambda represents dark energy, or the cosmological constant driving accelerated expansion. CDM indicates cold dark matter particles moving much slower than light speed when they decoupled from other matter in the early universe. The cold part is crucial. Cold dark matter can clump on all scales, from galaxy-sized halos to supercluster-sized concentrations. Hot dark matter particles moving near light speed, like neutrinos, wouldn't clump on small scales because high velocities prevent small-scale collapse. Observations showing galaxies forming early and structure existing on all scales favor cold over hot dark matter. Lambda CDM has been remarkably successful, predicting observed structure properties with precision. Structure formation proceeds hierarchically. Small structures form first, then merge into larger structures over time. This bottom-up scenario reflects how gravitational instability works in a cold dark matter universe. At early times, shortly after recombination, the first overdensities to collapse were small masses equivalent to thousands or millions of stars. These proto-halos formed within millions of years after recombination, allowing the first stars to form by 100 to 200 million years after the Big Bang. Small halos merged into larger halos over time. By 500 million years, the first galaxies assembled. By 1 to 2 billion years, galaxy groups formed. By 5 to 10 billion years, rich clusters assembled. The largest structures, superclusters, and great walls formed most recently, reaching current sizes only within the last several billion years. The cosmic microwave background provides initial conditions for structure formation. Temperature fluctuations measured by satellites like COBE, WMAP, and Planck show that when the universe was 380,000 years old, density variations of delta rho over rho, approximately 10 to the -5th, existed 1 part in 100,000. These variations had a specific pattern described by the power spectrum, a function showing fluctuation amplitude versus angular scale. The power spectrum peaks at angular scales around 1 degree, corresponding to the sound horizon. At recombination, the distance sound waves travelled in 380,000 years. Smaller scales show acoustic oscillations, peaks and troughs, reflecting sound wave compressions and rarefactions. This pattern is imprinted in the matter distribution, seeding structure formation. Gravitational amplification follows a simple principle. Overdense regions have stronger gravity, attracting surrounding matter and becoming denser. Initially, a region 1 part in 100,000 denser than average had negligibly stronger gravity. But as matter fell inward, density increased, strengthening gravity further in a runaway process. The growth rate depends on cosmic expansion in a rapidly expanding universe. Structures grow slowly because expansion opposes gravitational collapse. In the radiation-dominated era before 50,000 years after the Big Bang, expansion was so fast that density perturbations barely grew. In the matter-dominated era, from 50,000 years to 9 billion years after the Big Bang, expansion slowed, allowing perturbations to grow proportionally to the scale factor, doubling the universe's size, doubled density contrast. In the dark energy-dominated era, since 9 billion years ago, accelerated expansion slowed growth further. Dark matter's collisionless nature allows it to form tightly bound structures. Dark matter particles don't interact except through gravity. They pass through each other without colliding or exchanging energy. When dark matter falls into overdense regions, it doesn't heat up from collisions, allowing it to settle into compact halos. Ordinary matter, being collisional, gas atoms collide frequently, converts kinetic energy to thermal energy when it falls into halos, heating and expanding. The gas pressure prevents ordinary matter from collapsing as tightly as dark matter. This is why dark matter halos extend farther than visible galaxies. Galaxies' visible extent is limited by gas pressure, while dark matter extends much farther, creating a vast invisible halo surrounding each galaxy. N-body simulations model structure formation by following billions of particles under gravity. The Millennium simulation, completed in 2005 by the Virgo Consortium, tracked 10 billion dark matter particles in a cubic volume 2.2 billion light-years on a side. The simulation started with initial conditions matching CMB observations and evolved forward in time, following how particles moved under mutual gravitational attraction. Results showed dark matter organizing into filaments, walls, and halos, matching observed structures. The simulation predicted how many halos of different masses form, how halos merge over time, and how halos cluster spatially. Comparing predictions with observations validates lambda CDM. The model accurately predicts structure statistics without free parameters beyond those measured independently from CMB and expansion history. More recent simulations include gas physics. The illustrious TNG simulation, completed in 2018, followed 30 billion particles combining dark matter and gas. The simulation included physical processes affecting gas, gravitational heating, radiative cooling, star formation, supernova feedback, and black hole accretion. These processes regulate galaxy formation. Cooling allows gas to form stars, while feedback heats gas and prevents runaway star formation. The simulations produce synthetic universes, where galaxies form within dark matter halos, matching observed galaxy properties, including masses, sizes, colors, and star formation rates. The agreement between simulated and real universes across multiple properties validates both the dark matter model and our understanding of galaxy formation physics. The simulations reveal dark matter's distribution in detail. Dark matter halos aren't uniform spheres, but have density profiles. Density decreases with distance from center, following approximately a power law with modifications near the center and edge. The Navarro-Frenk-White profile, proposed in 1996 by Giulio Navarro, Carlos Frenk, and Simon White, describes halo density as ρ of r equals ρ s divided by the quantity r over rs times the quantity 1 plus r over rs squared. where Rs is a scale radius and ρs is a characteristic density. This profile fits simulated halos across a wide mass range, from galaxy-sized to cluster-sized halos. Observations of galaxy rotation curves, cluster mass profiles from gravitational lensing, and satellite galaxy distributions confirm this profile, providing evidence that simulations capture dark matter's behavior accurately. The dark matter halo mass function, the number of halos per unit volume, as a function of mass, is a key prediction testable by observations. The mass function is steep low-mass halos are exponentially more abundant than high-mass halos. For every cluster mass halo containing 10 to the 15th solar masses, there are about 10,000 galaxy mass halos containing 10 to the 12th solar masses. This steep distribution explains why small galaxies vastly outnumber giant galaxies, and why clusters are rare. Counting clusters and groups at different masses and redshifts tests whether the observed abundance matches predictions. Current observations show excellent agreement, with discrepancies at most a factor of 2 at extreme masses where statistics are poor due to small numbers. Dark energy's role in structure formation is primarily negative. It slows or halts growth. Dark energy's negative pressure causes accelerated expansion, increasing the rate at which space expands. Faster expansion means matter is carried apart more quickly, opposing gravity's attempt to pull matter together. Structures below a certain scale, regions where gravitational binding energy exceeds the work done by expansion, remain bound and continue collapsing. But structures larger than this scale, roughly 30 to 50 million light-years at present, won't collapse further. Dark energy increasingly dominates as the universe expands, raising this limiting scale over time. Eventually, no new structures will form, existing clusters will persist but won't merge, and the cosmic web will freeze in its current configuration as expansion overwhelms gravitational attraction on all scales not already bound. The interplay between dark matter and dark energy determines the universe's fate. In a universe without dark energy, gravity would eventually halt expansion and cause recollapse, the Big Crunch. Structures would continue growing indefinitely until the universe contracted. In a universe with dark energy as a cosmological constant, expansion accelerates forever. Structures stop growing once dark energy dominates. The largest structures that will ever exist are forming now or have formed. No structures larger than current superclusters will assemble. In trillions of years, dark energy will dominate so completely that even galaxies beyond our local group will recede faster than light, disappearing beyond the cosmic event horizon. The observable universe will shrink to include only gravitationally bound structures, while the universe as a whole continues expanding exponentially. The baryon acoustic oscillations measuring scale. Baryon acoustic oscillations, or BAO, are imprints of sound waves from the early universe frozen into the cosmic structure we observe today. These oscillations occurred in the photon baryon plasma before recombination at 380,000 years after the Big Bang. Sound waves, pressure oscillations driven by gravitational collapse fighting photon pressure propagated through the plasma at about 57% of light speed. The waves could travel a maximum distance equal to the sound horizon, to the distant sound, travelled in 380,000 years, approximately 490,000 light-years at that time. When recombination occurred, photons decoupled from matter, sound waves stopped, and the density pattern froze. This pattern is imprinted in both the cosmic microwave background and the matter distribution, creating a preferred scale in structure that serves as a standard ruler, a known physical size that appears at different angular sizes depending on distance and cosmic geometry. The BAO scale today, after accounting for cosmic expansion, is approximately 490 million light-years, or 150 megaparsecs in co-moving coordinates, the coordinates that expand with the universe, keeping proper distances between co-moving points increasing with the scale factor. This 150 megaparsec scale appears as a subtle excess of galaxy pairs separated by this distance compared to random expectations. Finding this excess requires surveying hundreds of thousands or millions of galaxies to accumulate sufficient statistics. The signal is only a few percent enhancement above random, easily masked by noise in small samples. Large surveys, like the Sloan Digital Sky Survey's BOSS and eBOSS components, and the ongoing Dark Energy Spectroscopic Instrument Survey, have measured BAO with high precision, providing crucial constraints on cosmic expansion history and dark energy properties. The BAO detection process measures galaxy clustering as a function of separation. Astronomers calculate the correlation function, the probability of finding two galaxies separated by distance r compared to random distribution. In a universe with BAO, the correlation function shows a peak at r approximately 150 megaparsecs, slightly more galaxy pairs separated by this distance than expected. Alternatively, the power spectrum, the Fourier transform of the correlation function, shows oscillations at specific wave numbers corresponding to the BAO scale and its harmonics. The peak or oscillation location precisely measures the BAO scale, which depends on cosmic expansion history through the integral of c over a times h of a from the observed redshift to present, where c is light speed, a is scale factor, and h is the Hubble parameter. The first definitive BAO detections came in 2005 from two independent teams analyzing SDSS data. Daniel Eisenstein and colleagues examined the clustering of 46,000 luminous red galaxies, finding a clear BAO peak at 150 megaparsecs with 4 sigma significance. Sean Cole and colleagues analysing the 2DF Galaxy Redshift survey with 221,000 galaxies detected a 2.4 sigma signal. Both detections confirmed predictions from CMB observations. The same acoustic scale visible in the CMB temperature fluctuations at 380,000 years appears in galaxy clustering today after being stretched by cosmic expansion. This consistency validated the hot Big Bang model and demonstrated that BAO provides a powerful cosmological probe independent of supernovae or other distance indicators. BAO measurements constrain cosmic expansion in two ways: transverse to the line of sight through angular diameter distance, and parallel to the line of sight through the Hubble parameter. The transverse BAO scale, how large 150 megaparsecs appears on the sky in angular units, depends on angular diameter distance to the observed galaxies. Farther galaxies show smaller angular sizes. Measuring the transverse BAO scale at various redshifts maps how angular diameter distance evolves with redshift, testing cosmological models. The radial BAO scale, how 150 megaparsecs appears in redshift space along the line of sight, depends on the Hubble parameter at that redshift, which converts redshift differences to distances. Measuring both components breaks degeneracies between cosmological parameters, improving constraints. The BOSS survey, operating from 2009 to 2014, measured BAO with unprecedented precision. BOSS observed 1.5 million galaxies spanning redshifts 0.2 to 0.7, covering the crucial epoch when dark energy began dominating cosmic expansion. At redshift Z equals 0. 57, BOSS measured angular diameter distance to 1% precision and Hubble parameter to 1.7% precision. These measurements confirmed lambda CDM predictions. The observed expansion history matches a universe with approximately 70% dark energy and 30% matter. The measurements also constrain dark energy's equation of state, finding W consistent with -1 within uncertainties, supporting dark energy being a cosmological constant rather than evolving dynamical field. The EBOS survey, operating from 2014 to 2020, extended BAO measurements to higher redshifts. EBOS observed 500,000 galaxies at redshifts 0.6 to 1 and 500,000 quasars at redshifts 0.9 to 2.2, probing the universe when it was 3 to 7 billion years old. The quasar observations used the Lyman alpha forest absorption lines in quasar spectra from intervening hydrogen clouds to measure BAO at Z approximately 2.4, looking back 11 billion years. Results showed that expansion history from Z equals 2.4 to present is consistent with lambda CDM. The full dataset, spanning Z equals 0.15 to 2.4, provided a detailed map of cosmic expansion over 12 billion years, confirming dark energy's dominance in recent epochs, while showing matter-dominated expansion at earlier times. The Dark Energy Spectroscopic Instrument, or DESI, which began science observations in 2021, will provide the next generation of BAO measurements. DESI observes 5,000 objects simultaneously using robotic fiber positioners on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona. Over 5 years, DESI will measure redshifts for 40 million galaxies and quasars spanning redshifts 0, 1 to 3.5, creating the largest three-dimensional cosmic map ever made. First-year data released in 2024 showed BAO detections with precision better than 1% at multiple redshift bins. Preliminary results suggested possible deviations from a cosmological constant, hints that dark energy's equation of state might vary with time, but the evidence is marginal, requiring more data to confirm or refute. BAO measurements complement supernova observations. Supernovae measure luminosity distances, how bright objects appear depending on distance and cosmic expansion. BAO measures angular diameter distances, and Hubble parameters geometric quantities less affected by astrophysical systematics that might bias supernova measurements, like dust extinction or evolution of supernova properties. Combining BAO and supernovae provides stronger constraints than either alone, breaking degeneracies between dark energy properties, matter density, and spatial curvature. The consistency between BAO and supernova measurements across different redshifts validates both methods and strengthens confidence that accelerated expansion is real rather than arising from observational systematics. The BAO technique has limitations at high redshift. At redshifts above Z, approximately 3, galaxies become faint and surveys detect only the brightest objects, typically quasars. Quasars are rare, providing sparse sampling that makes BAO detection difficult. The Lyman alpha forest technique extends BAO measurements to Z, approximately 2 to 3, but analysing the forest requires careful modelling of astrophysical effects, ionization state of intergalactic gas, temperature fluctuations, peculiar velocities that can mimic or distort the BAO signal. Despite challenges, Lyman alpha BAO measurements have been successful, detecting the BAO peak at Z approximately 2.4, with significance exceeding 3 sigma, probing expansion history during the crucial epoch when dark energy's influence was growing. Future BAO surveys will reach even larger samples and higher redshifts. The Nancy Grace Roman Space Telescope, launching in 2027, will conduct a spectroscopic survey of 50 million galaxies at redshifts 1 to 2 from space, avoiding atmospheric disturbances that limit ground-based spectroscopy. Euclid, launched in 2023, will measure redshifts for 50 million galaxies using slitless spectroscopy, measuring spectra for all objects in the field simultaneously. These surveys will measure BAO to sub% precision at redshifts 1 to 2, tightly constraining dark energy's evolution during the epoch when it began dominating. Ground-based projects like the Subaru Prime Focus spectrograph will add complementary measurements at similar redshifts. BAO measurements test modifications to general relativity. Some theories propose that accelerated expansion results not from dark energy, but from modifications to gravity at cosmological scales. Modified gravity theories predict different expansion histories than lambda CDM, particularly at intermediate redshifts. BAO provides a clean test because it measures geometric quantities, distances, and expansion rates directly related to spacetime geometry. If gravity is modified, BAO measurements would deviate from lambda CDM predictions in specific ways depending on the modification. So far, observations show no deviations, supporting general relativity's validity on cosmological scales and disfavoring many proposed modifications. The cosmic sound horizon, the distance sound travelled before recombination, can be calculated precisely from CMB observations. The sound speed was c divided by square root of 3, where c is light speed, determined by the photon-baryon plasma's equation of state. Integrating this speed over time, from the Big Bang to recombination at 380,000 years, gives the sound horizon approximately 147 megaparsecs in co-moving coordinates. After recombination, cosmic expansion stretched this scale by factor 1091, the ratio of the universe's current scale factor to the scale factor at recombination. Multiplying 147 megaparsecs by 1091 gives 147 megaparsecs in co-moving coordinates, which equals 490 million light-years in physical distance, the BAO scale observed today. This precise agreement between prediction and observation validates the hot Big Bang model and our understanding of early universe physics. The galaxy clusters as cosmic laboratories. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds to thousands of galaxies within regions 10 to 30 million light-years across. Clusters serve as cosmic laboratories where extreme conditions test physics under circumstances impossible to replicate on Earth. Hot gas-filling clusters reaches temperatures tens to hundreds of millions of Kelvin, so hot that electrons are stripped from atoms and the gas emits copious X-rays. This intracluster medium contains more mass than all the galaxy's stars combined, making clusters primarily composed of hot gas rather than stars. Dark matter dominates cluster mass, comprising 80 to 85% of total mass and providing the gravitational potential that binds clusters together. Studying clusters reveals dark matter properties, gas physics under extreme conditions, and provides crucial tests of cosmological models. El Gordo Spanish, for the fat one, officially designated ACT-CLJ 100-4915, is the most massive galaxy cluster known at high redshift. Located at redshift Z equals 0.87, corresponding to distance 7 billion light-years, El Gordo has estimated mass approximately 3 quadrillion solar masses, written as 3 times 10 to the 15th solar masses, making it comparable to the most massive nearby clusters, despite being observed when the universe was only 6.5 billion years old. The cluster shows evidence of a major merger, 2 massive clusters colliding at 2,200 kilometers per second, a speed second only to the bullet cluster merger among observed cluster collisions. The collision has displaced the hot gas from the dark matter, allowing separate measurement of gas and dark matter distributions through X-ray and gravitational lensing observations. El Gordo's extreme mass and early formation time challenge lambda CDM models, which predict very few such massive clusters should exist at Z approximately 0.9. The hottest cluster known is RxJ 1347, 5-1145, located at redshift Z equals 0.45, corresponding to distance 4.9 billion light-years. The cluster's gas temperature reaches approximately 300 million Kelvin in the central regions, the hottest gas discovered in any cluster. Such extreme temperature indicates a very deep gravitational potential well, implying enormous mass. The cluster's total mass is approximately 2 quadrillion solar masses. The high temperature results from gas compression during cluster assembly and possibly from shocks generated during recent mergers. Observations show complex structure, including multiple temperature peaks, suggesting ongoing dynamical activity. The cluster is also notable for its brightness in X-rays. It's one of the most luminous X-ray sources among clusters, making it easily detectable despite its significant distance. The most distant massive cluster confirmed is JKCS 041 at redshift Z equals 1.9, corresponding to distance approximately 10 billion light-years and look-back time to when the universe was only 3.8 billion years old, 27% of current age. The cluster contains at least dozens of confirmed member galaxies, with total mass estimated at 600 trillion solar masses, making it a rich cluster despite forming so early. Discovering such a massive cluster at Z approximately 1.9 was unexpected. Lambda CDM predicts that clusters this massive should be extremely rare at such early epochs, because insufficient time had passed for structure formation to assemble such large masses. However, statistical analysis shows that finding one such cluster in the surveyed volume is marginally consistent with predictions, though more discoveries of similarly massive high redshift clusters would challenge the model. X-ray emission from clusters provides crucial information about gas properties. The intracluster medium, heated to tens or hundreds of millions of Kelvin, emits X-rays through thermal Bremsstrahlung free electrons, accelerating in ions' electric fields, emit photons. The emission rate depends on gas density squared and temperature denser. Hotter gas emits more X-rays. Chandra X-ray Observatory and XMM Newton satellite observations map X-ray emission across clusters, revealing gas density and temperature distributions. The gas temperature indicates the gravitational potential depth. Hotter gas requires deeper potential, revealing total mass including dark matter. Observations show gas density peaks near cluster centers and decreases outward, while temperature often shows complex profiles reflecting merger history and gas physics. Gravitational lensing by clusters magnifies background galaxies, allowing observations of objects too faint to detect otherwise. Massive clusters, with total mass several quadrillion solar masses, create sufficient lensing to produce multiple images or giant arcs, background galaxies stretched into long curves. The Hubble Space Telescope has observed dozens of lensing clusters, revealing hundreds of multiple images and arcs. The most powerful lensing clusters magnify background galaxies by factors of 10 to 50, enabling detection of galaxies at redshifts Z equals 6 to 10 distances, 12 to 13 billion light-years, when the universe was less than 1 billion years old. These lensed high redshift galaxies provide insights into early galaxy formation impossible to obtain without lensing magnification. The Bullet cluster, formerly designated 1E0657-56, located at redshift Z equals 0.296, corresponding to distance 3.8 billion light-years, provides the most direct evidence for dark matter. Observations show a smaller cluster has passed through a larger cluster at 4,700 km per second, one of the fastest cluster collisions ever observed. The collision displaced the hot gas, which collided and slowed, separating from the galaxies, which passed through without significant interaction. Gravitational lensing maps show mass concentrating where galaxies are, not where hot gas is, demonstrating that most mass is dark matter associated with galaxies rather than hot gas. This spatial separation of mass from gas provides clear evidence that dark matter exists as a distinct component beyond ordinary matter. Cluster abundance evolution tests cosmology. The number of clusters at different masses and redshifts depends sensitively on cosmological parameters: the amplitude of initial density fluctuations, the amounts of dark matter and dark energy, and expansion history. More initial fluctuations produce more clusters. More dark matter makes clusters form earlier and more abundantly. More dark energy suppresses cluster formation at recent epochs. Counting clusters from X-ray or optical surveys provides counts versus mass and redshift. Comparing observed counts with predictions tests whether lambda CDM correctly describes structure formation. Current results show general agreement, with some suggestions of 10 to 30% discrepancies at highest masses, though systematic uncertainties in mass measurements complicate interpretation. The Sunyaev-Zeldovich effect provides another method for detecting clusters. When CMB photons pass through hot cluster gas, some photons scatter off energetic electrons through inverse Compton scattering, gaining energy and shifting to higher frequencies. This creates a distortion in the CMB spectrum, fewer photons at low frequencies below 218 GHz, more at high frequencies above 218 GHz. The effect's amplitude depends on gas temperature and total electron content along the line of sight quantity called the Compton parameter. The effect is redshift-independent distant clusters create the same signal as nearby clusters of equal mass, making it powerful for finding high redshift clusters. Surveys like the South Pole Telescope and Atacama Cosmology Telescope have discovered thousands of clusters through the Sunyaev-Zeldovich effect. Cluster mergers provide insights into dark matter properties. During mergers, dark matter halos pass through each other because dark matter is collisionless. Particles don't interact or slow significantly through collision. Gas, being collisional, slows and heats through shocks. Observations of merging clusters, like the Bullet cluster showing spatial separation between dark matter and gas, constrain dark matter's interaction cross-section. If dark matter self-interacts strongly, halos would slow during mergers similarly to gas. Observations show no significant slowing, setting upper limits on self-interaction cross-section, less than 1 square centimeter per gram for dark matter particle mass, around 100 gigaelectron volts. These limits constrain dark matter particle properties, ruling out strongly interacting candidates. Clusters at different redshifts reveal structure formation's history. At Z greater than 1.5, clusters are smaller and less massive. Typical masses around 100 to 500 trillion solar masses, compared to 1 to 3 quadrillion solar masses for the most massive nearby clusters. Cluster galaxies at high redshift show more active star formation blue colors, indicating recent star birth compared to nearby clusters dominated by red elliptical galaxies with little ongoing star formation. This evolution reflects clusters assembling hierarchically over time through mergers, with galaxy properties transforming through interactions and gas stripping. Comparing cluster properties at different epochs tests whether structure formation proceeds as lambda CDM predicts, providing powerful constraints on cosmological models. The galaxy cluster scale 10 to 30 million light-years represents the upper limit of gravitationally bound structures. Clusters remain bound despite cosmic expansion because their internal gravitational binding energy exceeds the work done by expansion trying to pull them apart. Structures larger than clusters, superclusters, and great walls aren't bound and expand with the universe, only slightly slowed by mutual gravity. This makes clusters the largest objects that will persist indefinitely into the future. Dark energy prevents larger bound structures from forming and will eventually pull apart even superclusters, but clusters remain stable. In trillions of years, clusters will survive as isolated islands in an exponentially expanding universe, with everything beyond each cluster's gravitational domain receding faster than light. Future cluster studies will improve cosmological constraints. The eROSITA X-ray telescope, launched in 2019, is conducting an all-sky survey detecting over 100,000 clusters, dramatically increasing the sample. The Vera-C, Rubin Observatory's legacy survey, will discover tens of thousands of clusters through optical imaging. The Simons Observatory in CMBS-4 will detect thousands of clusters via the Sunyaev-Zeldovich effect with high sensitivity. Combining these datasets, X-ray, optical, and Sunyaev-Zeldovich allows measuring cluster masses precisely and testing whether different methods agree. Improved mass measurements will tighten cosmological constraints, potentially revealing tensions between cluster abundance and CMB predictions that might indicate new physics beyond lambda CDM. Clusters remain one of cosmology's most powerful probes, testing structure formation on the largest gravitationally bound scales. The large-scale structure simulations. Large-scale structure simulations are computational models following the evolution of billions of particles under gravity and gas physics, creating synthetic universes that can be compared with observations. These simulations start with initial conditions matching the cosmic microwave background, a distribution of particles with density fluctuations of 1 part in 100,000 at 380,000 years after the Big Bang. The simulations then evolve forward in time, calculating gravitational forces between particles and updating positions and velocities. Over simulated billions of years, the initially nearly uniform distribution fragments into filaments, walls, voids, and clusters the cosmic web. Modern simulations incorporate dark matter dynamics, gas physics including heating and cooling, star formation, supernova feedback, black hole growth, and numerous other processes. The most sophisticated simulations produce synthetic universes, closely matching observations, validating theoretical understanding of structure formation. The Millennium Simulation, completed in 2005 by the Virgo Consortium, was a landmark in cosmological simulation. The simulation followed 10 billion dark matter particles in a cubic volume 2.23 billion light-years on a side large enough to contain representative samples of galaxy clusters and superclusters. Each particle represented 860 million solar masses of dark matter. The simulation used 512 processors of the IBM P690 supercomputer at the Max Planck Society's computing center in Garching, Germany, requiring about 1 month of continuous computation. The simulation tracked structure evolution from redshift Z equals 127 when the universe was 100 million years old to present. Results showed dark matter organizing into the cosmic web with statistical properties matching observations halo mass functions, clustering amplitudes, and filament distributions all agreed with data. The Illustris simulation, completed in 2014, added hydrodynamics following gas in addition to dark matter. Illustris simulated a cubic volume 350 million light-years on a side with 1.8 billion dark matter particles and 1.8 billion gas cells. Including gas required simulating additional physics: gravitational heating as gas falls into potential wells, radiative cooling as gas emits radiation and loses energy, star formation when gas density and temperature meet criteria for collapse, supernova explosions, returning energy and metals to gas, and black hole accretion with associated feedback. These processes regulate galaxy formation. Without feedback, gas would cool and form stars too efficiently, producing galaxies more massive than observed. With feedback tuned to match observations, Illustris produced galaxies with realistic properties. Illustris TNG, completed in 2018, improved on Illustris with better resolution and more sophisticated physics. The largest Illustris TNG volume simulated 820 million light-years on a side with 30 billion particles, 18 billion dark matter particles, and 12 billion gas cells. The simulation included updated black hole feedback models, where supermassive black holes at galaxy centers drive powerful winds that expel gas from galaxies, preventing excessive star formation. The simulation also included magnetic fields, tracking how magnetic field lines stretch and amplify during structure formation. Illustris TNG produced galaxies matching observations across multiple properties: galaxy masses, sizes, star formation rates, colors, gas content, and clustering. The simulation demonstrated that lambda CDM, combined with reasonably well understood astrophysics, can explain observed galaxy populations. The Eagle simulation, completed in 2015 by an international collaboration, took a different approach, calibrating feedback parameters to reproduce specific observations. Eagle simulated volumes up to 330 million light-years on a side with 6.8 billion particles. Rather than predicting galaxy properties from first principles, Eagle adjusted parameters controlling supernova and black hole feedback to match observed galaxy masses and sizes at z approximately 0.1. The calibrated model was then tested against observations at other redshifts and other properties not used in calibration. Eagle successfully reproduced galaxy color distributions, star formation histories, gas metallicities, and intergalactic medium properties, demonstrating that a consistent model can explain diverse observations if feedback is properly included. Comparing simulations with observations tests the lambda CDM model. Simulations predict the galaxy two-point correlation function probability of finding pairs of galaxies separated by various distances. Measurements from SDSS and other surveys show correlation functions at different redshifts. Simulations match observations at large scales above 10 to 20 million light-years, where gravity dominates and astrophysical uncertainties are minimal. At smaller scales, comparisons are complicated by baryon physics, star formation, and feedback affect small-scale clustering. Agreement at large scales confirms lambda CDM describes gravitational structure formation correctly. Discrepancies at small scales provide information about feedback processes that simulations must model accurately. Dark matter-only simulations, which don't include gas, are computationally cheaper and probe larger volumes. The Millennium XXL simulation, completed in 2011, followed 302 billion dark matter particles in a volume 13 billion light-years on a side approaching the observable universe's scale. Such enormous simulations are necessary for studying the largest structures and rare objects like the most massive clusters. Dark matter-only simulations predict dark matter halo distributions, which can be populated with galaxies using models connecting galaxy properties to halo properties. This hybrid approach, simulating dark matter, then adding galaxies with models, allows predictions for galaxy clustering in volumes too large for full hydrodynamic simulations. Simulations predict cosmic structure at high redshift, testable by observations from JWST. The James Webb Space Telescope, launched in 2021, observes galaxies at redshifts Z equals 10 to 13 distances, 13.2 to 13.4 billion light-years, when the universe was only 300 to 450 million years old. JWST has discovered galaxies at these epochs more massive and brighter than many simulations predicted, causing some tension. If confirmed with additional observations, overly bright, high redshift galaxies might indicate that star formation proceeded more efficiently in early galaxies than models assume, requiring adjustments to feedback prescriptions. Alternatively, systematic errors in mass estimates or unusual initial mass functions might reconcile observations with predictions. This tension is an active research area. The cosmic web's properties in simulations match observations. Filament, lengths, widths, and number densities in simulations agree with galaxy survey measurements. Void size distributions match observations. Simulations predict many small voids, fewer medium voids, and rare supervoids, just as observed. Cluster abundance versus mass and redshift matches observations within uncertainties. The agreement is quantitative, not just qualitative statistical measures like power spectra and correlation functions match to few % precision across wide ranges of scales and epochs. This detailed agreement validates lambda CDM and the simulation methods, giving confidence that simulations capture the essential physics of structure formation. Machine learning techniques are enhancing simulation interpretation. Simulations generate vast datasets, positions, velocities, temperatures, and densities for billions of particles at hundreds of time snapshots. Extracting scientific insights requires analyzing this data efficiently. Neural networks can be trained on simulations to predict properties like galaxy colors or star formation rates from dark matter halo properties, bypassing expensive hydrodynamic simulations. Machine learning can also identify structures like filaments and voids in simulations and observations, allowing quantitative comparisons. These techniques accelerate research by automating analyses that previously required custom programming for each scientific question. Future simulations will push toward larger volumes and higher resolutions simultaneously. Exascale supercomputers, machines performing 10 to the 18th calculations per second, enable simulations with trillions of particles in volumes approaching the observable universe's size while resolving individual galaxies. The illustrious TNG 300 simulation resolved galaxies, but covered only 820 million light-years. Future simulations will cover 3 to 5 billion light-years while maintaining comparable resolution. These simulations will predict rare objects like the most massive clusters or longest filaments testable by LSST and other surveys. They'll also model cosmic variance, how structure varies between different regions of the universe, allowing better interpretation of observations from surveys covering limited volumes. Simulations also model alternative cosmologies, testing what universe would look like if lambda CDM were wrong. Simulations with different dark energy equations of state, different dark matter interaction cross-sections, or modified gravity show how structure formation changes. Comparing these predictions with observations constrains alternatives to lambda CDM. For example, warm dark matter particles with higher velocities than cold dark matter suppresses structure on small scales. Simulations show warm dark matter produces fewer small galaxies and more diffuse halos. Observations of dwarf galaxies and small-scale structure rule out warm dark matter masses below about 3 to 4 kilo-electron-volts, favoring cold dark matter. Such tests demonstrate simulation's power for distinguishing between cosmological models. The cosmic expansion limiting future structures. The future of cosmic structure is determined by the competition between gravity pulling matter together and dark energy driving accelerated expansion pulling space apart. Current understanding suggests dark energy is a cosmological constant with equation of state W equals -1, causing expansion to accelerate exponentially over time. This acceleration prevents new large-scale structures from forming and will eventually tear apart structures not tightly bound by gravity. The epoch of active structure formation, when the largest structures could grow, ended several billion years ago, as dark energy's density overtook matter density and began dominating cosmic dynamics. Today, structures larger than approximately 30 to 50 million light-years won't collapse. Further dark energy's expansion overwhelms gravitational attraction on these scales. Existing superclusters and great walls are frozen in their current configurations, expanding with cosmic expansion rather than collapsing. The critical scale separating bound from unbound structures depends on the balance between gravitational binding energy and expansion work. A structure is bound if its gravitational self-energy exceeds the kinetic energy from cosmic expansion. For a spherical overdensity with radius r and mass m, binding occurs when gravitational potential energy approximately equals g times m squared over r exceeds expansion. Kinetic energy approximately equals h squared times m times r squared, where g is Newton's gravitational constant and h is the Hubble parameter. Solving for critical radius gives r critical approximately equals g times m divided by h squared. For masses around 10 to the 15th, solar masses typical cluster masses, and current Hubble parameter Haas-Rho, approximately 70 km per second per megaparsec. The critical radius is roughly 10 to 20 million light-years. Clusters with radii below this remain bound. Larger structures are unbound. Dark energy's dominance began at redshift Z, approximately 0.4, corresponding to 4.3 billion years ago, when the universe was 9.5 billion years old. Before this epoch, matter dominated its density, exceeded dark energy density, allowing gravity to drive structure formation efficiently. At Z approximately 0.4, matter and dark energy densities were equal. After this transition, dark energy dominated and expansion accelerated, slowing structure growth. Structures that hadn't collapsed by Z approximately 0.4 had little time remaining to do so. The largest structures forming now the final great walls and superclusters are the last of their kind. Structures attempting to form in the future will be disrupted by accelerated expansion before they can collapse. The cosmic web has nearly reached its final configuration. The future evolution of unbound structures involves their gradual dispersal. Superclusters, like Laniakea, spanning 520 million light-years, are too large to remain bound against dark energy. Galaxies within Laniakea flow toward its center in the Norma cluster region, but dark energy prevents most from actually reaching the center. Instead, galaxies in full velocities will slow, halt, and reverse as dark energy increasingly dominates. In tens of billions of years, Laniakea will dissolve galaxies, that were falling together will recede from each other as expansion carries them apart, faster than gravity pulls them together. The structure will gradually fade as galaxies disperse, leaving only isolated bound clusters separated by ever-increasing distances. Galaxy clusters, being tightly bound, will survive indefinitely. Clusters like Coma, Virgo, or Perseus have binding energies far exceeding expansion work at their scales. Galaxies within clusters orbit at hundreds to thousands of kilometers per second within regions only 10 to 20 million light-years across. These velocities and compact sizes ensure gravity dominates. Clusters will continue accreting matter from their immediate surroundings, small groups and isolated galaxies within a few tens of millions of light-years. But they won't merge with other clusters separated by hundreds of millions of light-years. Each cluster becomes an isolated island universe, gravitationally bound, while the space between clusters expands exponentially. The local group containing the Milky Way, Andromeda, Triangulum, and dozens of dwarf galaxies will merge into a single galaxy. The Milky Way and Andromeda are currently approaching at 110 kilometers per second and will collide in about 4 billion years. Computer simulations show the collision will disrupt both galaxies, ejecting some stars into tidal tails, while most stars settle into a giant elliptical galaxy containing 800 billion to 1 trillion stars. Triangulum will merge with the Andromeda Milky Way system within a few billion years after the initial collision. Dwarf galaxies will spiral inward through dynamical friction, merging with the giant elliptical or being tidally disrupted. Within 10 billion years, the local group will be a single massive elliptical galaxy, sometimes called Milkomeda. The observable universe will shrink over time. The particle horizon, the boundary of the observable universe, continues expanding as more time passes for light to reach us. Currently, at 46.5 billion light-years, the particle horizon will grow to about 60 billion light-years over the next trillion years. But the event horizon, the boundary beyond which events can never affect us, is shrinking in co-moving coordinates. Currently, at about 16 billion light-years, the event horizon represents the farthest distance from which light emitted today will eventually reach us. Objects beyond this distance recede faster than light due to dark energy's acceleration. Their light travels toward us, but space expands faster, carrying the light away. Over time, the event horizon shrinks, encompassing progressively smaller co-moving regions. In approximately 150 billion years, all galaxies beyond the local group will have receded beyond the event horizon and disappeared from view. Observers in Milkomeda will see a dark universe containing only their own galaxy and no others. The cosmic microwave background will have redshifted to microkelvin or nanokelvin, temperatures effectively undetectable. The expansion of space will have diluted the CMB photon density to near zero. Future astronomers will have no evidence of the Big Bang, cosmic expansion, or the larger universe. They might conclude the universe is static, eternal, and contains only their galaxy, a perspective similar to astronomers' understanding before Hubble's 1920 seconds discoveries, demonstrating how cosmology depends on epoch of observation. Dark energy's nature determines long-term fate details. If dark energy is a cosmological constant, expansion accelerates exponentially, and the universe grows forever, becoming exponentially emptier and colder. Bound structures like Milkomeda survive indefinitely, slowly evolving through stellar evolution and black hole formation. Stars exhaust nuclear fuel, becoming white dwarfs, neutron stars, or black holes. After 10 to the 14th years, star formation ceases as gas is exhausted. After 10 to the 20th years, stars eject from galaxies through gravitational interactions or fall into central black holes. After 10 to the 40th years, protons might decay speculatively, causing matter to disintegrate. After 10 to the 100th years, black holes evaporate through Hawking radiation, leaving empty space approaching absolute zero. If dark energy is phantom energy equation of state W less than -1, the universe ends in a big rip. Phantom energy's density increases over time, causing ever faster acceleration. Eventually, expansion becomes so rapid that it overcomes gravitational binding on all scales. Clusters are ripped apart as expansion overpowers their gravity. Then galaxies disintegrate as expansion overcomes stellar orbits. Then solar systems are torn apart. Then planets dissolve as expansion overcomes molecular bonds. Finally, atoms are ripped apart as expansion overcomes electromagnetic forces. The Big Rip occurs in finite time, perhaps 20 billion years, if W equals -1.5, though current constraints suggest W is closer to -1, making the rip unlikely. Observations will constrain W more precisely, determining whether this fate awaits. If dark energy decays into matter or radiation, a possibility in some models, accelerated expansion might end. Dark energy density would decrease over time, eventually falling below matter density. Expansion would decelerate again, allowing new structure formation. Future galaxies and clusters could form from matter ejected during the dark energy epoch. This scenario seems unlikely given that dark energy appears consistent with a cosmological constant, which by definition doesn't decay. But physics beyond the standard model might allow dark energy decay. Future observations measuring dark energy's evolution will test whether decay occurs. If dark energy is truly constant, the universe's large-scale structure has reached its peak. No larger structures will ever form. The cosmic event horizon's shrinking creates a fundamental limit to future knowledge. Objects crossing the horizon are lost forever. No signal from them will ever reach us. The horizon currently recedes at light speed in our reference frame, but in co-moving coordinates it shrinks, encompassing fewer galaxies over time. This means information is continuously lost as galaxies cross the horizon. Information about their subsequent evolution becomes forever inaccessible. The universe beyond the horizon continues existing and evolving, but we can never observe it. The observable universe becomes progressively smaller in co-moving volume, even as proper volume expands exponentially. This isolation is a direct consequence of dark energy's acceleration. Absent dark energy, no event horizon would exist, and all of space would eventually become observable given sufficient time. Understanding structure formation's endpoint requires understanding dark energy. Current observations constrain dark energy's properties, but don't reveal its fundamental nature. Is it truly a cosmological constant vacuum energy from quantum fields, or a dynamical field that might evolve? Does it represent a fundamental energy component, or a modification to gravity? These questions will be addressed by experiments like the Vera C, Rubin Observatory's Legacy Survey, the Nancy Grace Roman Space Telescope, and Euclid, which will measure cosmic expansion, history and structure growth with unprecedented precision. Better measurements will either confirm dark energy is a cosmological constant, solidifying predictions about structure's future, or reveal deviations indicating more complex physics that might change fate projections. The largest structures ever found, the Great Walls, superclusters, and cosmic web, represent structure formation's culmination, the grandest organization matter achieved before dark energy halted growth.